Well, so then we start the Virasoro amplitude section here with a talk by Maria Nocchi, who will talk about exact results for string amplitudes in ADS. And so you have 30 minutes and some questions.
Yeah.
Yeah, okay.
Okay,
so as you please. You're not sensible to
So, in the meantime, if you haven't yet picked your seat at the conference dinner, please do ASAP and before the end of the first break. Otherwise, we'll have to assign you randomly and you may not like it. I'm not threatening, but you know.
Okay, so then let's welcome Maria Nocchi another time. Some more people have arrived and we hope for more audience still. And she will talk about Virasoro amplitudes.
thank you so much. Well, good morning, everyone, and thank you so much to the organizers for the possibility to share my research today with you. I'm not strictly working with integrability, but I'm trying to find the interplay between bootstrap techniques in the SCFT and integrability, so I'm going to try to report on some exact results for string amplitudes in ADS. So it's going to be a summary of some papers with, is this on? Okay, with Fernando Aldaime, supervisor in Oxford, Tobias Hansen, Aurélie Sangaré, Clément Virali, and Shinanzu. So I'll start by trying to motivate why string amplitudes are interested in ADS. And immediately after that, I will focus on the high energy limits and what we can learn about them. This will lead us to present building blocks of ADS string amplitudes in ADS, but this is going to be just the last part of the talk because it's a bit more technical and mathematical. So I'm just going to focus on the high energy limits and in particular on the Regge limit, where the interplay with integrability is more evident. And I'll conclude with some key takeaways and future directions. Okay, so very basically, we're going to study scattering amplitudes. They are basic objects lying at the interface between particle physics, mathematics, and string theory, and more. And they are predictive tools giving us the probability for a certain process to happen. But for us, they will especially be important because they allow us to uncover structure and invariant symmetries that may not be evident from a Lagrangian formulation. Today, we're going to focus on string scattering amplitudes in flat space. So in flat space, we have a well-established setup, which is the perturbative string theory. And in principle, we have worksheet methods that allow us to study any amplitude as a sum over topologies, namely punctured Riemann surfaces of increasing genus with insertions of vertex operators that corresponds to your initial and final states. So very schematically here, what we have is an integral like the metrics and the fields, as usual in path integral formulations. And importantly, we have this sum over topologies. So for 3 level, which is the topic of today's talk, we're going to have a Riemann surface with insertions of vertex operators of these states lambda I. And then we're going to expand in the powers of the string coupling constant. So we're going to take it small to consider weakly coupled strings. Essentially, we have 2 parameters, GS, which is the string coupling constant, set to 0, and then alpha prime, which is going to be very important. And it gives you a sense of the size of the string. So we have to think that as alpha prime is tuned to 0, for example, this is the point particle limit. And then we take alpha prime corrections or equivalently stringy corrections. We're going to investigate, for example, the alpha prime to infinity limit, which is the very stringy or high energy behavior and something in between. An important point, even just in flat space, is that sometimes this sum is dominated by a saddle point, allowing us to make exact computations. And we're going to be back to this even in ADS. Now, an outstanding question is, what about curved spacetimes? And if you take any standard formulation from flat space and try to extend this to a general curved background, it's very difficult to do so. And at the moment, even if in principle there is a perturbative genus expansion, there is no direct worksheet approach available, even at 3 level. So we need to make progress somehow. In our favor, we have a DSCFT, which allows us to describe string scattering amplitudes in ADS from CFT correlation functions of the boundary theory, where we can use the beautiful setup of like CFT techniques and so on. We also have exact limits that can teach us a lot about the more complicated theory in ADS. First of all, we have the flat space limit, which is going to be our starting point to develop the theory in ADS. But we also have high energy limits where computations can be done exactly. So we do need additional tools to make progress in this setup. We want to study amplitudes of strings in ADS. The main context is going to be ADS CFT, but there is so much more helping us to make progress. So we're going to use a bootstrap approach. But as I was stating, we're going to focus on flat space limits and high energy limits and what we can learn and infer about the worksheet structure of ADS. And integrability definitely has a role here, giving us information about the polar structure of the amplitude, as I was going to try to explain. But even number theory from a mathematical point of view is going to be fundamental here because it is going to be the right language to describe the structure of strings in ADS. So lesson to learn. Studying tractable limits such as flat space or high energy will help us build intuition for the full theory. So let's start. We focus on the paradigmatic example of ADS5 cross S5, dual 2 for dn equals 4 super Mills. And even in the presence of a maximally supersymmetric setup, alpha prime corrections, so stringy corrections, are very challenging to compute. And the Virasoro-Shapiro program in ADS was born a couple of years ago with Fernando, Tobias Hansen, and Joao Silva, and with the aim of learning how to analyze and including curvature corrections in ADS. The main object of study is the scattering of 4 gravitons at 3 level, so we have a Riemann surface with 4 punctures. In flat space, this is the very well-known Virasoro-Shapiro amplitude. It's one of the outstanding results in string theory. And even if it was not the original form, now we know that it can be written as a worksheet integral of this kind, where Z is the cross ratio on the sphere after you use conformal invariance to fix 3 points. As we go to ADS5 cross S5, we don't know how to quantize perturbative string theory on this setup, but we do have a DSCFT, which tells us that this is the correlator of 4 stress tensor multiplets to leading order in a large central charge expansion. And here, S, T, and U are the Mandelstam variables, so the kinematic invariance of your strings. If you carry out this worksheet integral, you get the very beautiful and neat ratio of gamma function here. But maybe a less appreciated representation here is the following, which is very illuminating because it tells us about the structure of the amplitude, mathematically speaking. And to be precise, you can notice that as you expand the amplitude, you're going to get some very special numbers, which are called zeta values. And I will define them in a minute. But not just zeta values, you get odd zeta values. And these are the ones which are single-valued. This maps to the single-valued nature of this worksheet integral. Indeed, if you look at the integrand, it is single-valued as you move around the puncture on the worksheet. So single-valued is something which is evident in flat space, and we're going to stick to that. More specifically, if you do the low-energy expansion, so alpha prime to 0, I said before that alpha prime is the size of the string, so alpha prime to 0 is really the point particle limit, so no surprise that this is a supergravity result. But then we have an infinite tower of stringy corrections. So these Wilson coefficient alpha, they live in the ring of single-valued zeta values, and this is very deep. The idea of Fernando, Tobias, and Joao was to assume that this is also the case for ADS corrections. So it is a conjecture, but we're going to see that we have a lot of evidence for that. And this led to a precise proposal for the structure of the amplitude in ADS5 cross S5, which is the following. First of all, the amplitude in ADS is defined as an expansion around flat space. So we are expanding in alpha prime over R squared, where R is the radius of ADS, and we include perturbatively in 1 over R, the curvature corrections. And at each order, the correction take the form of a genus 0 worksheet integral, exactly as in flat space, but now with insertions of a weight 3K single-valued multi-polylog. So these W are just the insertions of polylogs. I'm going to define them in the next slide. And this provides an algorithm that allows us to compute each ADS correction modulo input from integrability. And what this means is that while for the first curvature correction, it is enough to impose single-valuedness, the structure of poles, and so on, to fix it completely in a bootstrap setup, starting already from the second correction, we need input and help from integrability. For example, giving us like the dimensions of Konishi-like operators will fix the structure of the poles. So let's very briefly present the building blocks of this ansatz. We have a multiple polylog. This is labeled by word W with letters in some alphabet, and the length of the word is called weight. These are recursively defined by these differential equations and these boundary conditions, where E is the empty word, and then we have an alphabet of letters forming the word W. So as an example, for example, if you have all zeros as the letter, this will reproduce for you the powers of logs, while less trivial example, if you have a strings of 0 and the 1, this is just the classical polylogs, and then you have much more. So to sum up, these are just analytic functions of a single complex variable, which are multi-valued on the complex plane. So you will have branch cut at 0 and or 1. What we can do is to consider linear combinations of polylogs such that all the branch cuts cancel, and these are going to be our single-value multi-polylogs. So we act with a single-value map on the multi-valued one, and it will return to us the single-valued one, wherever that is. A very simple example, the log of z, of course, is multi-valued on the complex plane, but you can just add the log of z bar, and it will give you a single-valued extension to that. But this can be done more generally for any multiple polylog, and by now we know the perfect classification to any weight, thanks to Francis Brown. An important lesson here is that at any given weight, there is a finite dimensional vector space of available functions, which makes them very interesting in terms of an ansatz, of course. And the very last piece of information that we're going to need for today is that zeta values can be defined as multiple polylogs at 1. So this is precisely the sense that I was mentioning before, such that like the zeta values at odd integers are the ones which are single-valued, because if you try to make the same for even integers, they just vanish. So it's really non-trivial. And this also motivates this structure, because the multiple polylogs, the single-valued ones, are the right functions, such that upon integration over the Riemann sphere, they will return to you the single-valued zeta values, exactly as in flat space. So single-valuedness is our guiding principle and our key assumption here. So now we have two questions. On one side, we would like to determine the amplitude in ADS to all orders in 1 over R. On the other side, we would like to make connections to more direct worksheet computations, which is what is lacking in ADS. And turns out that the strategy to reply to both these answers simultaneously is to focus on more accessible limits, and in particular to the high energy limits, which provide a lot of insight into the full theory. So let's start. First, we investigated the high energy limit. In this limit, I take S and T, the Mandelstam variable, to be large, and keep S over T fixed, the scattering amplitude. We have a dual perspective. On one side, we could take the point of view from space-time. Already in flat space, back to the 80s, Gross and Mann had this beautiful result about strings in high energy limit. And we know that the path integral is dominated by a classical solution, which is the following, and importantly, it is single-valued on the worksheet. What we did in this paper with Fernando and Tobias is to extend this to ADS by proposing a classical scattering problem in ADS, a bosonic model actually, and we proposed an algorithm to solve the equation of motions in 1 over R to any order in 1 over R. And the solution takes this form, where L are just a linear combination of single-value multipolylogs. So again, they are the right building blocks of the answer. But we also have the worksheet point of view. In flat space, if we go back to the worksheet integral, so here, if S and T are large, we can just do a saddle point approximation, and the saddle point is S over S plus T. But most interestingly, even for the full ADS Virasoro-Shapiro amplitude, each curvature correction is just a rational function in S and T, so it cannot modify the location of the pole in a 1 over R expansion. So we are done, because we have it from flat space, so this is the result in flat space. The answer in ADS is just going to be the same thing times the integrand evaluated on the saddle point. And by requiring that the two predictions agree, we find this very nice and compact result. So curvature corrections exponentiate to each order in S squared over R squared fixed. And the key point is that only the subleading correction is relevant in this limit, and it's really all we have to say. And I just wanted to mention that the same structure of multiple polylogs turns out to be the case for other backgrounds in ADS, as Shai will review. And this high energy limit is found to be exactly the case even in those backgrounds. So it's highly non-trivial. Then we investigated the richer limit, which is the Regge limit. So T is still large, but S is finite. And what we found with Fernando, Cleman, and Shinan is that to all orders, the amplitude can be written as derivative of the flat space Regge limit. And this is really the interplay with integrability, because we all know that the big achievement of Regge theory is that you need only the leading trajectory in cubic couplings to fix the entire amplitude. But here, these operators are the Konishi-like operators, which are a target of integrability. So what we did is to write the ADS Virasoro-Shapiro amplitude in the Regge limit just in terms of the CFT data of these exchange operators. So the OPE coefficients, and these are related to dimensions of these operators in n equals 4 super-Yang-Mills as strong coupling. And this operator R is the effect of the curvature of the background. It's a differential operator, so its derivatives with respect to the spin J. And in 1 over R, we have a way to fix it to any order because it satisfies a difference equation. And as you can see, derivatives with respect to J will eventually eat T to the J, which is the flat space result in the Regge limit, producing powers of logs. So we're always going to have logarithmic corrections in T, and this reflects the fact that in ADS, perturbatively in 1 over R, you have higher order poles. So what we can do now? We can infer some results that are exact, again, in 1 over R. First, we can resum all the leading logs, and leading logs exponentiate, matching the high energy result in the right regime. But we can do more. We can resum the subleading logs. And this is extremely simple with respect to the other computations. And moreover, it provides an all-order results in the limit of large RT with log cube T over R squared fixed. So again, this is a regime where exact computations can be done. We can do even more. And now that we have the Regge limit from these derivatives of flat space perspective, we can try to understand what this implies for the worksheet and how can we go back to the full theory. So first, knowing the Regge limit in ADS, we can ask ourselves what is the manipulation that we need to do to the integrand such that it reproduces the Regge limit. And this is the right limit to engineer. We send T to infinity, Z to 0, while keeping T times Z fixed. So this is going to be the worksheet integrand in the Regge limit that reproduces the right Regge limit. And indeed, it matches perfectly with the prediction. But we can do even more, and now reverse our logic and look for the right integrand without knowing what was the proposal. So I told you that the proposal for the full amplitude is in terms of single-value multipolylogs, but let's forget about that and just ask ourselves, what is the right integrand that we need to put to reproduce the right Regge limit, which is derivatives of the flat space answer. And since we have derivatives with respect to j, we need to insert a function which is expanded in powers of logs of modulus of z. Indeed, if you imagine to just put log of modulus of z here, this is just derivative with respect to j of this factor, right? So we need to do that. And what this implies beautifully is this functional equation for the right insertion in the Regge limit. That's our prediction from the other computation that I showed. And again, this is known to any ordering 1 over r. So this fixes families of solution for the worksheet integral to all orders in the curvature expansion. This is deep, lastly, for the reason that this is a single-valued log. So it is manifestly single-valued around 0, which is a nice confirmation, if you wish, of the full ansatz. And the single-value log is the symptotic of single-value multipolylog, so we have a nice independent check of the full answer. So lesson to learn from this second part is that the high-energy limits are a natural step toward an ADS worksheet theory, enabling us to probe the theory's mathematical structure across different regimes. And driven by this, now we're going to propose a mathematical structure of the ADS string amplitudes. Can I ask you how much time I have left? OK, perfect. So as usual, we start from flat space, which is our starting point, but also like inspiration for methods in ADS. And now we forget about the specific theory, and we just want to extract the building blocks, mathematically speaking. It's a bit abstract, but I think really nice. So for closed strings, we have this function, which is called complex beta function. And it's exactly the same as like Virasoro-Shapiro amplitude, but without the 1 over u squared factor. So now we are really not thinking about the theory. And this evaluates to the ratio of gamma function. Similarly, now we can extend to open strings. And open strings are now given by the other beta function, which is now a one-dimensional integral from 0 to 1, giving another ratio of gamma function. And this would map to the Veneziano amplitude, for example. One of the most beautiful and significant relations of Euler and complex beta functions are that they are related by a single-valued map, very much like the single-valued map between polylogs and single-valued polylogs. So we can think of the complex beta, or equivalently the closed string case, as the single-valued map of the open string amplitude. And if you want, this can be rephrased in terms of the KLT relations. So back to the 80s, this very nice relation were proposed about the relation between perturbative closed string amplitudes at tree level and bilinears of open string amplitudes. So the square of the beta function gives you the complex beta function up to this kernel. And this kernel is not just a random function, of course. It's very non-trivial that it exists at all, because you have to think that you want to reproduce like a physical answer on the left-hand side. So this kernel needs to cancel all the spurious poles and gives the right zeros. So this is really amazing that it exists, even in flat space. Yeah.
There has to be some function, right? Because if you're writing a function s and t equals another function s and t, that will always be true for some other function s and t. So I guess, like, what are the special properties of that kernel which make it more interesting than just in a random?
Yeah. Well, as I was saying, like, for example, if you have Yang-Mills that squares, like Yang-Mills and gravity, they have very different poles. But for example, if you have double poles on one side, then the kernel needs to cancel exactly the double pole.
Didn't there have to be a kernel by construction? I mean, you're relating two functions. Like any two functions are related by a third function, right?
Yeah, of course.
So I guess, like, so why is it so surprising that such a relation exists?
I guess, I mean, you don't know what's the double copy, right? You take any single copy theories, and you don't know what to expect. But there is one function which gives you gravity, and it's universal, moreover, right? If you change the single copy, it's still the same function. So it is special, I think. Thanks. So motivated by what I explained before, now the proposal is that the building blocks of ADS string amplitudes are the same kind of worksheet integrals, so generalization of Euler and complex beta function, with insertions now of polylogs. Single-value multipolylogs for closed strings, and multiple polylogs for open strings. So what we are looking for is now a single-value map, or a KLT kind of relation, between this generalization of Euler and complex beta function. So if you want, we are looking for something like this. And this is, I think, the most technical slide of the talk. But as usual, we need to pick the right language to get a nice answer. And the right language in this setup is to study the generating functions. So if you want, like we're used to this in physics and maths, but for example, for multiple polylogs, you can put them all together in a generating function that as you expand in something will give you the multiple polylog at any weight. And here, the expansion is in E0 and 1. They are two non-commutative variables that are associated with the letters 0, 1 of the alphabet that I was introducing before. So you do this kind of game for the building blocks of a DS open and closed string amplitudes. So curly J and curly I are the generating function of our building blocks. So at each order in E0 and E1, you pick J or I, and this is the proposal for that weight. So what we are after is a KLT relation between the generating function, because this encapsulates all the weights. And the kernel itself, of course, by construction, is going to be an expansion in the non-commutative variables. What we find, quite remarkably, I think, is that the kernel, even in ADS, takes a very simple and elegant form, which is the following. M0 and M1 are the monodromy matrices found by Francis Brown, governing the discontinuities of multiple polylogs as we cross the real line. And more explicitly, if you wish, to all orders, we find that this is the inverse of the kernel in ADS, to each order in E0 and 1. It's a bit technical, but if people are familiar with KLT relations, it's also the case in flat space that the inverse of the kernel is even more interesting because it is related to physical amplitudes. So not only it's an interesting function, but if you study the inverse of the kernel, it encapsulates the information about scattering of cubics, scalars, and so on. Turns out that even if we don't understand it yet, even in ADS, the inverse of the kernel is a very beautiful and compact formal, which is much easier to deal with. And it takes this form. So we have cotangent pi s plus E0, so shift by E0 and shift by E1, but we have this non-trivial like multiplication by z that I didn't introduce, but it's just the generating functions of multiple zeta values. So if you want the same generating functions of polylogs, but at 1. And as you expand in E0 E1, this reproduces exactly the inverse of the kernel in flat space. So if you go back to this, the inverse of that is the cotangent. So it's exactly that, but this is an all-ordered prediction. So at each order in E0 and 1, it will give you the right kernel in ADS. Of course, a lot remains to understand about this. I think I will conclude by giving you some key takeaways and leaving you with future directions. So I try to present some results about this program of how to compute string amplitudes in ADS from alternative tools. We said there is no worksheet theory that, and we need to make progress somehow. So ADS-CFT definitely helps, but we need a lot of help from integrability, number theory, and exact limits. So first, the single valuedness has a central role here, exactly as in flat space, but we don't understand it. So flat space is an evidence, but I think even more in ADS, it's a guiding principle. Turns out to be correct because all the predictions match perfectly with integrability and localization results, but a lot remains to be understood. Also, we can do exact computations in the energy limits, and they give us insights on the full theory and the nice interplay with integrability. This led us to uncover the mathematical structure of string amplitudes in ADS. We just started looking at that and trying to extend the beautiful relations in flat space to ADS, which was not done at the level of the string theory yet. And as some future directions, some of them are really beyond my area of expertise, but I leave them there. First, it would be nice to try to understand to which extent we can combine, for example, the energy results with integrability and the structure of the solution to go to higher orders in 1/R. See if there are nice patterns, now that we also know how to do the integrals themselves. And definitely we need to understand more about these KLT relations, like to focus on specific amplitudes and try to see what's there. Of course, the ultimate goal would be to find a direct string theory computation that would map and match our results, hopefully, but this is still open. And maybe I'll leave you there with, it would be amazing to develop a quantum spectral cal for the DS Virasoro-Shapiro amplitude and really try to exploit the nice interplay with integrability. With this, I will thank you for your attention.
Well, amazingly, we're back on schedule, right? I mean, you were even about to crack. So we have time for questions.
Could you explain again maybe what it exactly means to compute an open string amplitude on ADS5 times S5? I mean, you're not doing type 1 string.
No, of course. So here I'm not referring to ADS5 cross S5. The last piece was really just ADS in general, like a background in ADS. Of course, for open strings, you need a different background, like ADS5 cross S3, and like you need to do some supersymmetry. I think maybe Shai will mention something later, but here I was just really saying that motivated by the results for the open and closed strings in ADS, we proposed that this would be the general structure in ADS. Of course, then to do specific computers, you need to specify the right background in ADS, the right compact space, and so on.
So this statement about the kernel is just a statement about function spaces that I can compose.
Yeah, definitely, 100%. Then it's still work in progress. Focusing on specific computers seems very non-trivial to get it there. Thanks.
Thanks.
More questions?
Hi, Maria. Thank you for your very nice talk. I have a question about high-energy limit. Have you considered construct the vertex operator in this high-energy limit?
We have not.
Already have this.
So for this case, like the details about vertex operators are subleading in this limit. So you don't really need to know them exactly, but people are working on vertex operator even like at finite SNT. It's highly non-trivial in ADS5 cross S5.
Thank you.
Thanks.
Gadi?
So some of your assumptions are kind of may not be specific to ADS5 S5. For example, signal validness. Do you think if you consider just string theory in asymptotically flat space, you should get similar?
Sorry?
If you consider string theory in asymptotically flat space, bosonic string theory, and compute for graviton scattering,
like with single validness.
curvature expansion, would you think you should get similar single validness property?
I don't know. This is really like inspired by the fact that for closed strings in flat space, you have these asymptotics which contain single valid zetas. So now if you look at the worksheet, you need to have polylogs to get them.
Maybe it may be actually true that if you...
Maybe, yeah.
It may be generic fact.
I don't know actually.
Yeah.
It could be the case, yeah. It is really a conjecture, like a driving assumption. It turns out to be there, but at least from my perspective, we don't understand the physics of that. So I don't know how this is specific to ADS versus asymptotically flat space.
Can I ask one little point? If you just bring up your final inverse kernel.
Yeah.
So what's blue and what's not blue in that format?
So this is I just wanted to make the comparison with flat space.
Right.
So here...
You said these are the bits which are not in flat space. Okay, I get it.
Yeah, that's flat space, and then that's how to uplift.
My misunderstanding. Thanks. Do we have other questions? Then let's thank you again for this nice talk.
Thanks.
Sure. Yeah, we can zoom it, but it's...
No, I think it's not on. Oh,
it's on, but it should be... If you could like bring it down a bit.
like this?
Yeah, that's already... It's good if you can keep it like
Okay,
that.
all right.
And...
Let me try.
Oh, sorry. Okay, here's a pointer. Do you want to check?
This is... Okay, and then this is the light. Okay, perfect.
So, right. So for the second talk, we welcome Shai Chester, who will equally talk about Virasoro-Shapiro amplitudes.
Oh, well, thanks for the invitation. This is my first time at one of these big integrability meetings, so it's exciting to meet this new community for me.
This talk will be based on a few recent papers with my postdoc Deliang Zhong, who will be becoming a faculty in Beijing in a few months, as well as Tobias Hansen. And of course, this whole program was started by Fernando, Tobias, and Joao a few years ago, as Maria already mentioned. Okay, so let's begin by discussing Virasoro-Shapiro amplitude. So in flat space, Virasoro-Shapiro amplitude is the most basic quantity in string theory. In some sense, it's the defining quantity of string theory. And so as Maria mentioned, it's given by the simple ratio of gamma functions, where ST and U are Mandelstam variables in 10 dimensions. So this amplitude describes scattering of closed strings at tree level, which means the leading order in string coupling, but dimensional integral, and this is because you can actually compute this integral using the string theory worldsheet, which is why this was one of the founding quantities in string theory. So what are some basic properties of this Virasoro-Shapiro amplitude? So first of all, it has poles in ST and U that correspond to the massless graviton multiplet, as well as a tower of massive string modes. Another basic property, which Maria discussed, is the high energy limit, where S and T are both big with fixed ratio, in which case it exponentiates. This is in contrast to amplitudes in field theory, where they would also go to 0, but they would go to 0 polynomially. It's only in string theory that they go exponentially. That's one of the key differences. Another property is that in the low energy expansion, when S and T are small, it takes the following form, where the leading term would just be a field theory amplitude for graviton scattering. But then you have these infinite corrections, because you have a string, which basically correspond to these massive modes. And as Maria discussed, these are all proportional to single-valued zeta functions. These correspond to higher derivative corrections. So this would be the r to the 4 correction, the d to the 4 to the 4 correction, etc. Okay, so we're going to be discussing string theory in ADS. And the obvious motivation, as everyone knows, is that that is the only non-perturbative definition of string theory that we have so far. So the classic examples of ADS CFT are type 2b string theory at ADS 5 crosses phi, which is dual 10 equals 4 super 8 mils. You have 2a string theory at ADS 4 cross CP3, which is dual to this 3 ABJM theory. And finally, 2b string theory at ADS 3 crosses 3 cross M4, which is dual to some D1, D5 CFT, although we know very little about that CFT. So it's kind of the most mysterious example. So in this duality, closed string scattering in the bulk is dual to correlators of some operator in the CFT, which is oftentimes the stress tensor multiplet. For instance, tree-level scattering in string theory would be the same as the leading order 1/n term of the CFT correlator, which is what integrability people usually care about, because they care about the planar limit. So even though we have this duality, which in principle tells us how to compute ADS scattering, in practice we don't know how to do it, because ADS backgrounds involve Ramon-Ramon flux. And we don't know how to do worldsheet string theory in the presence of Ramon-Ramon flux. Hopefully in the future, maybe we'll figure out how to do that using the pure spinor formalism or string field theory. But at present, we don't really know how to do it. On the CFT side, it's also hard, because the CFTs are always strongly coupled with large n. So it seems like we don't know how to do it on either side. Nonetheless, this talk is going to be about how we've made progress using ADS CFT. So in this talk, we're going to bootstrap ADS Virasoro-Shapiro amplitude and expansion around flat space for each of these classic ADS CFT pairs that we discussed in the previous slide. And it all comes from two assumptions, this program. The first assumption is that the amplitude expanded in ADS around flat space is given by this flat space limit formula, which is basically a Borel transform of the CFT correlator. So this is an assumption, because in the strict flat space limit you can prove this. But once you apply this formula beyond the flat, is given by a worldsheet integral of certain single-valued multi-poly logarithms. Maria reviewed the detailed form of these guys. And basically, by combining these two functions, it uniquely fixes the answer for the first ADS correction. So this program was first done for ADS 5 by Fernando, Tobias, and Joao. And then in these recent papers with my co-authors, we generalized it to ADS 4 as well as ADS 3. And so it's kind of, it was kind of miraculous that it worked in ADS 5, and you might have thought maybe there's some weird coincidence. The fact that it works in every possible background means clearly there's something going on. Indeed. Well, in that case, I'm not sure if you have a CFT with enough supersymmetry such that you could do this program. But in principle, I mean, this is related to Arkadiy's question before, which is that the assumption of writing things as a single-valued multi-poly logarithm, it might work in any background. It's just we only have enough control to check that so far in these very symmetric backgrounds. But indeed, it'd be good to maybe try for weirder backgrounds. Anyways, So the way this connects to integrability, which is what this conference is about, is that from this ADS expansion, you can extract CFT data of single trace operators at large lambda, such as the Konishi operator, and this you can directly compare to integrability. And so that's going to be one of the themes of this talk. Okay, so first let's discuss what these holographic correlators look like on the CFT side. So these are CFT operators dual to graviton modes in ADS. And we're giving a very general discussion which will work in any dimension to show how kind of it's the same idea. So the idea is that you expand a correlator of these operators in superconformal blocks, which is fixed by superconformal symmetry. And so the 4-point function will always be written as the sum over these superblocks, one for each multiplet, plus some protected terms. I'm separating this into two terms because the protected terms are multiplets where the scaling dimension is fixed, and these are not going to be relevant for the expansion we consider, because the expansion we consider is going to be for very high scaling dimensions. And then the terms here, these are going to be the multiplets where the scaling dimension is not fixed. These are called long multiplets, so usually they're not protected by supersymmetry, and their scaling dimension can take any value. And so for specific theories, these super blocks are linear combinations of regular blocks, which corresponds to the fact that a super multiplet is just a combination of regular conformal multiplets. And you could fix this purely kinematically. It's been done in many different examples in many different dimensions. And so remember, these are the ones we're going to care about because we care about large scaling dimension for this expansion around flat space. So the next, okay, so that was purely non-perturbative. Now we take the large n limit, and when you take the large n limit, it's convenient to express your CFT correlator in Mellon space. So Mellon space is basically a Fourier transform which respects conformal symmetry. And so you have two variables in position space, u and v, so that means you're going to be now relating it to two variables in this Mellon space, which are s and t. And so as in any Fourier transform, you're going to have these powers of u, like the one variable to the power of the other variable, for each of the two variables. These precise factors are basically what makes the Mellon space correlator convenient. But I mean, mathematically, you could have put different factors. And then you have this gamma functions that you insert into the definition. And the motivation of doing this is that in Mellon space, with these precise factors, poles in ST and U correspond to the scaling dimensions of exchanged operators in a large n expansion. So if you write down Witten diagrams, the scaling dimensions correspond to these poles. And so at tree level, we know from large n that the only exchange diagrams we should have are single trace and double trace. And so a convenient way of just taking care of all the double trace poles is putting in these gamma factors. Because then the resulting Mellon amplitude only has poles for single trace operators, which makes it much simpler. So this is just a convenient choice. Okay, so first we do this exact transformation, which again is non-perturbative. Now we expand in n, and we're going to define this m of s and t as the planar limit of this CFT correlator, which is what integrability people care about. So this Mellon amplitude in the planar limit includes two kinds of terms. The first term we call supergravity is going to be meromorphic in S and T. So it has poles in S and T, which correspond to the exchange of operators in the supergravity multiplet. So this is all the single trace exchanges. All these other terms, these are polynomials in S and T. So these are not exchange diagrams. Instead, these are contact diagrams. And you have infinitely many of them. And these correspond to higher derivative corrections to supergravity. And so the coefficients of these contact terms depend on lambda, the tuft coupling, which you could just think of as basically the ADS radius divided by the string length in some abstract sense. And basically the goal is to compute all these b's, because this is where all the dynamical information is in these b's. So this one is totally fixed, and you're trying to compute these b's for these various contact terms. If you can compute all the b's, then you totally understand this planar ADS amplitude. Okay. So now, so far we've done the correlator in Mellon space and the large n expansion. Now we're going to talk about how to expand this planar correlator in flat space into ADS. And so for this, we use this formula introduced by Penidonis 15 years ago, this flat space limit formula. And so what this formula is doing is you're taking your Mellon amplitude, you're rescaling the Mellon variables by lambda, and then you're making lambda very big, where lambda, remember, is the tuft coupling, which is related to the ADS radius. So that's the sense in which you're making the ADS radius big. And then, as Penidonis showed in his paper, the way to properly take a flat space limit is you do a Borel transform. In some sense, there had to be some kind of Borel transform because, like, this is an asymptotic expansion, and so to get something finite, you had to do some kind of transformation. Borel transform is usually the thing that makes it finite. And so this formula again works in general dimensions. So this D is for general CFT dimension D. This delta O is for any scaling dimension of the external operator. A very general formula. So this formula was derived rigorously in the strict flat space limit. So the first assumption, which we emphasized before, is that this exact same formula should also apply to ADS corrections to flat space, which is a wild assumption, but as you will see, it gives the right answer. Yes? Sorry, what is delta O? This is the scaling dimension of the external operator. So you have a 4-point function of O. Yeah. Yeah, we're making them all equal, yes. So that's why it's just delta O. I mean, you can do also non-equal, but for simplicity, we're talking about equal. Okay, so what does the CFD data look like when expanded around flat space? So as I mentioned, the flat space expansion you could think of physically as very high energy, and so that means you're only looking at very high dimension operators. So that means you should expand your CFD data. So this is the twist, which is scaling dimension minus spin, and this is the OP coefficient of these operators. And you expand it such that at large lambda, it's going like lambda to the quarter. So this quarter should be familiar to all these integrability experts in the audience, because that's how Konishi looks like at large lambda. The quarter basically comes from dimensional analysis, because it's basically 10 minus 2 is 8, divided by 2 is 4. And this is why these things scale like lambda to the quarter. You can work out the dimensional analysis later. And so this is the case basically in every ADS-CFT example. Similarly, this OP coefficient, it's convenient to take out this factor of sine squared and 4 to the tau. The reason why you have this sine factor with all these poles is basically because you have some kind of mixing between single trace operators and very high dimension double trace operators. And so that's why you expect to have poles. But this also just falls out naturally when you apply this formula to the block expansion. So just to reemphasize, the only operators that we care about expanded around flat space are very high dimension operators. So all the protected operators, we don't care about. We just ignore them. That's why we only care about these long multiplets. So now that we have this prescription to do the ADS expansion around flat space, we can apply this to the correlator. So you have your correlator. It was written as a block expansion. So first you take the Mann transform. Then you apply this Borel transform. And you will get the blocks expanded. And so this is what the blocks will look like when you expand them. So your block expansion, of course, you have the OP coefficient squared as usual. And then the blocks themselves, in terms of these Mandelstam variables, you expand them in 1 over lambda. And these are going to have various poles in S and T. OK, so this is the first part of the algorithm. All we've done is apply this Borel transform to our CFT correlator to expand it around flat space. OK, so the second assumption, as mentioned before, is we assume that this ADS amplitude is given by a worldsheet integral of a certain form. So in the strict flat space limit, you had this integral, but this was just 1. And so now we assume that for the ADS correction, you have the same kind of integral, two-dimensional integral, except now, instead of having 1, you're going to have an ansatz, which is the single-valued multi-polylogarithms of a certain weight multiplied by polynomials in S and T of a certain degree. So some brief motivation for why you have these weights in these degrees. So for the first ADS correction, we say you have weight 3 single-valued multi-polylogarithms. Now, why is that the case? That's basically because when you did the block expansion on the previous slide, which is purely kinematic, you get blocks which now have poles in S, T, and U. And you can just check that in the first ADS correction, you have poles up to degree 4. And so that means whatever your ansatz is here, after doing this integral, it should also only give poles up to degree 4. And it turns out that restricts the weight to be 3. Because there's some connection where it's like weight W gives poles of W plus 1. And so this is why we couldn't have single-valued multi-polylogarithms of any higher weight. In principle, you could have had lower weight, but not higher weight. If you have higher weight, you would have to go to the next ADS correction. Now, why do you have polynomials of a certain degree multiplied by these guys of a certain weight? That's because when you do the low energy expansion, you expect that the degree of these polynomials should be related to the weight of the zeta function that they multiply. So for instance, in flat space, we know that r to the 4 term is zeta of 3, and that multiplies degree 0, which is just 1. And then similarly, d to the 4r to the 4, which is zeta of 5, that multiplies s squared, degree 2. And so we assume that there's a similar correlation between the degree of the polynomial and the weight of the single-valued multi-polylogarithm once you go to ADS. So this is the motivation of this ansatz. And so now all we do is we compare this ansatz with unfixed coefficients of the polynomial to the block expansion from the previous slide, and it turns out that uniquely fixes the answer for the first ADS correction, which is kind of a miracle, because there's no reason why that had to work. I mean, first of all, the ansatz could have been totally wrong, and even if it was right, it could have been that it only fixed some of the coefficients. And so it turns out we're very lucky that it just fixes everything. And that this works in every single dimension. So now we're going to go into the specific examples for each theory. So let's start with n equals 4 super Yang-Mills. So in this case, we're going to consider the correlator of the stress tensor multiplet. So the first ingredient is just the superblock expansion. That was worked out for us by Dolan and Osborne, blessed memory, from 25 years ago. And remember, we only care about these unprotected multiplets, and in this specific correlator, they come in basically one family. So you have long multiplets of even spin, which are all in the singlet of the R symmetry. So for instance, for spin 0, this is a single trace multiplet called the Konishi, which is very popular in this community. So the scaling dimensions of these spin L single trace operators, in fact, have been computed from integrability in a series of very impressive papers by Nikolay and various other people. And so far, using integrability methods, they have the first 3 ADS corrections to the CFD data. So in particular, they have this large lambda expansion up to 1 over lambda to the 5/4, which from my understanding basically comes from taking this quantum spectral curve, numerically evaluating it from any different values of lambda and reading off a fit and guessing reasonable numbers that should appear in that fit. So other information which is known about this correlator is you can also compute it at large n and lambda using conformal bootstrap plus localization, which is totally analytic. This is the analytic bootstrap. And this has been done to the first 3 orders, and that allowed you to compute the full correlator up to the d to the 6 r to the 4 term, which basically means 1 over lambda cubed. So this is the information we have so far. So we have precise data about the single trace scaling dimensions, and we have also precise data of the full correlator up to a certain order in 1 over lambda. Although, of course, in this limit, you only really have access to the double trace operators. This limit doesn't tell you anything about single trace. OK. So now the new results that you get, and everything here was done in the papers by Fernando, João, and Tobias. So once you fix the first ADS correction, A1, you can now extract the first 1 over lambda correction to this lowest Regge trajectory. So when spin is 0, this is Konishi. So you get the expected flat space answer. You get this kind of shift. And then you get this non-trivial 1 over lambda correction. And this precisely matches integrability. So this was one of the first non-trivial checks that this program actually makes sense, which is that you get a precise prediction, which exactly matches what Nikolay and other people did many years back. So the nice thing about this Virasoro-Shapiro program, though, is that you get not only the scaling dimension, but also the OP coefficient. And so when the OP coefficient was first computed, there was no prediction. So it was a totally new result. Since Fernando's paper came out, though, there was this beautiful work by Simon Ekhammar, Frank, and Zara, which Frank spoke about yesterday, where they basically did numerical bootstrap plus localization plus integrability in the Plater limit, and they were able to numerically compute OP coefficients, and lo and behold, it exactly matches the prediction from this ADS Virasoro-Shapiro. So I would say there's overwhelming evidence that the assumptions used to get this answer are correct. Even more evidence comes from doing the low energy expansion of the ADS correlator up to d to the 4 r to the 4 order, in which case you can precisely match it to the predictions that Silvio and I made using bootstrap and localization. And in fact, if you combine all these things together, you can actually go to d to the 8 r to the 4 order, which is the first unprotected order, which itself is very conceptually interesting. Because you would have thought analytically that maybe you could only compute protected terms, which would be d to the 6 r to the 4 and smaller. But it turns out that with Fernando's assumptions, you can go beyond protected terms and get d to the 8 r to the 4, which shows that you're really putting in something conceptually new. OK, so these are all the results for ADS 5 crosses 5 I'm going to talk about. So now moving on to ABJM in 3D. So now we're considering the correlator of a stress tensor multiplet with n equals 6 supersymmetry. So the superblock expansion in this case is much more complicated. It was worked out by me and Silvio and collaborators 4 years ago. So now you have several different kinds of long multiplets. So the long multiplets, they're all R symmetry singlets, but they differ because you have 2 discrete symmetries that are relevant to this correlator. So one of the discrete symmetries is parity, and the second discrete symmetry is something we call Z, where this Z basically, it's like replaces SO6 by O6. So it's kind of an enhancement of the R symmetry, and it turns out that ABGM has this discrete symmetry, which is actually something that people weren't aware of until our paper. OK, so we can organize the long multiplets. So when spin is 0, you have 2 long multiplets. They're both Z even, but one can be parity even, one can be parity odd. When the spin is odd, you only have 1 long multiplet, which is Z even and parity even. And then when the spin is even and bigger than 0, then you have 3 long multiplets, which can be parity and Z even, parity and Z odd, or parity odd but Z even. So it's because of these discrete symmetries that you have different long multiplets. So this is more complicated than 4D, where you just basically had 1 family of long multiplets. So people have also computed the quantum spectral curve for ABJM, and so they also had some predictions at large lambda for scaling dimensions of single trace operators. So their predictions in their paper were for the odd spin guys, so this guy, and also for spin 0, Z even. But they did not have predictions for Z odd or these other examples, which I suspect is probably because they didn't know of the existence of the Z symmetry. So hopefully now in the future, there can be predictions. I think it should probably be possible for quantum spectral curve. So also using bootstrap and localization, analytically, we also have the large N and large lambda expansion, which for this correlator, we have up to R to the 4 term, which means the 1 over lambda to the 3 halves prediction. So this is the data which existed prior to this work. OK, so we do the same algorithm as before, which is that we compare the block expansion to this ansatz. It fixes the first ADS correction, and we can read off CFD data. So we can read off the twists of these lowest Regge trajectories, but we have different lowest Regge trajectories now. So we have one for odd spin, we have one, and then for even spin, we can be either Z even or Z odd. Now, I should note that in this planar limit, you're actually not sensitive to parity, which is why I'm not talking about parity here, but you are sensitive to the Z symmetry. So and this is why we get different answers for all three. So as you see, you get different numbers here, 21, 9, everything else looks kind of similar, and then this one is totally different. So for the ones for which integrability had computed the answer, we match integrability, which is very non-trivial, but we also have new predictions, which is the odd guys as well as, the even guys for Z odd, as well as the Z even for spin bigger than 0. So these are all new predictions. We also have new predictions for OP coefficients, which maybe could be studied using some analog of Frank's work, but now in 3D. OK, so that's all I'm going to say about ABJM. So now we can move on to ADS3. So in this case, we consider the correlator of the unique half BPS multiplet with small n equals 4 supersymmetry that's dual to the dilaton. So here we're not talking about graviton scattering, because there's actually a simple closed string scattering, which is dilaton scattering. But it's the same idea for the most part. And so just to emphasize, there's many half BPS multiplets in this D1, D5 CFT, but there's only one of them, which is dual to the dilaton. That's the one we look at. Why do we look at this specific one? Because then our results are not sensitive to this compact spacetime M4, which means that it applies to any theory with small n equals 4 supersymmetry. So in particular, it applies to either the K3 theory or the T4 theory. It's the same answer in both cases. So the first part of our algorithm, as usual, is you need to know the superblock expansion. Now, I should emphasize we're not doing like Virasoro symmetry here. We're just going to do global symmetry. We don't need Virasoro symmetry. Thankfully, the block expansion was worked out a few years ago by these authors in 2021. Similar to 4D, the long multiplets in this correlator, they all have even spin, and they're all in the singlet of the R symmetry, and then the protected multiplets we don't care about as usual. So the block expansion is very similar to 4D. One novelty of ADS3 is that the ADS CFT dictionary is a bit more complicated, in that in this duality, you have both D1s as well as F1s. Similarly, you have NS5 as well as D5. So you could turn on the flux for either the fundamental strings or its NS or its S dual. And so that means you have two kinds of fluxes in your ADS CFT dictionary. So this is the NS flux, which is k squared, where k should be an integer. And then this is the usual Ramon flux, similar to what you would have in higher dimensions. So that means a priori, our algorithm could be applying to the mixed flux case. We haven't yet specified if we're doing Ramon or NS or some kind of combination. OK, so now, so the first part of the algorithm is the block expansion. The second part of the algorithm is we assume a worldsheet ansatz. And from that, we can read off the first ADS correction and then read off CFD data. So for the lowest Regge trajectory, this is the answer we get. This matches flat space. This is the first 1 over lambda correction. So integrability has not yet been performed for this theory. I mean, there's some partial results, but there's no quantum spectral curve, which allows you to read off 1 over lambda corrections. And so instead, we had to use a somewhat earlier approach, which is a semi-classical expansion, which was first pioneered by Arkady and then many follow-up papers, where basically you compute some classical string solution at large quantum number and then boldly extrapolate to finite quantum number. In ADS5 crosses 5, that actually matched the results from integrability, similar in ABJM, so we kind of trust this method. And so applying the semi-classical method to ADS3 crosses 3, you get a prediction for what this answer should be. And so as you see, this prediction matches our answer if we set this quantum number j, which is related to the R symmetry, to 1, and if we also assume that the one-loop correction is -1/4. And so this is like a partial check of our results, because it doesn't check it completely, but it checks some of the terms. The fact that j equals 1, this is kind of consistent with the super multiplet you have, so that kind of makes sense. And then the fact that the one-loop correction is seated is -1/4, that's very interesting because it's actually the exact same one-loop correction that you get in both ABJM and ADS5 x S5. So I don't know if there's a reason why that's the case, but that's something we observe. And then we can also read off OP coefficients the same order. One last thing I will say is that when you do the semi-classical expansion, you can now input into that expansion whether it's Ramon-Ramon, an SNS, or some combination. And so this is why we know that our answer must correspond to the pure Ramon-Ramon case, because we are matching this answer for pure Ramon-Ramon. It would have given a different answer if it was mixed or an SNS. But that's the only way we know, because from the perspective of our algorithm, like we never really put in the fact that it was pure Ramon-Ramon. Okay, so in conclusion, we have fixed the first ADS correction to flat space for all the classic examples of ADS-CFT, which is ADS3, ADS4, and ADS5. In all these cases, we have predictions for scaling dimensions and OP coefficients of the lowest Regge trajectory. For ADS5, this matches previous results from integrability as well as bootstrap. For ADS4, you can compare some of the predictions to integrability, and it matches, but some of them are new. And of course, the OP coefficients are all new. And then finally, ADS3 is in some sense the most interesting, because the least is known about ADS3 from integrability. So basically, everything we have is a new prediction, both scaling dimensions and OP coefficients. I didn't really talk about this so much, but you could also take the low energy expansion of this ADS correction, and you could compare this to localization. For ADS4 and ADS5, this matches the expectation. For ADS3, there's no localization, so it's just, again, an entirely new prediction. Furthermore, we get new predictions for unprotected terms for ADS4 and ADS5. So in the remaining minutes, because I started a bit late, I can talk about future directions. So first of all, it'd be nice to get higher ADS corrections. So this was already accomplished for the second ADS correction for ADS4 and ADS5. So in my paper with Deliang and Tobias, and this one with the previous paper by Fernando and Tobias, to get the next ADS correction, it's not just automatically fixed. You have to put in extra data. So you have to put in some known results from integrability and localization. That's why it's harder to do for ADS3, because we don't have any known results. So of course, it would be nice to compare more things to integrability. So for instance, the Z-odd guys for ADS4, which I think some people are working on. For ADS3, it'd be nice to get the answer for mixed Ramon-Ramon and NS flux. So actually, as of 2 weeks ago, I think we actually solved this, although we're still checking some things. And so basically, the idea is that you have to generalize your worldsheet ansatz. So because previously we were using the same worldsheet ansatz that we had used in ADS4 and ADS5, and it turns out that, as Lawrence had suggested to me several months ago, you break worldsheet parity once you have mixed flux, and so you want to generalize your ansatz to include parity-breaking terms. We did that, and indeed, it seems to give the right answer, although we're still checking some things. Now, the reason why we think the ADS3 case is so interesting is that if you look at the pure NS example, which is just setting, it still applies to the flat space limit. In this case, in principle, the RNS formalism works. So you should be able to compute this correlator in pure NS. It hasn't been done yet, but in principle, you should be able to do it. And then, in principle, that should then give us a very powerful constraint on our ansatz, much more powerful than you have in higher dimensions where you don't know anything. And so that's why we suspect that it might be possible maybe to compute all ADS corrections for mixed flux by using this as an input. So ultimately, ADS3 might be even better than higher dimensions. Another thing we'd like to do is the large n=4 case, which is ADS3 crosses 3 crosses 1. And for this, we need a new warded entity to compute the superblocks, which is something we're working on. Finally, one thing I want to emphasize to this community is that so far you guys have applied integrability to almost all the known examples of holographic duals. So you've done n=4, you've done ABJM, and you've done the D1-D5 system. And then you've done various deformations. But there is one other example of ADS-CFT, which is completely different from the other examples. It's not just a deformation. It has a weak coupling limit in the gauge theory. It has a Tuft limit on the string theory side. It has a supergravity, which is completely understood. So this theory is basically ready to integrate. It has all the classic properties of integrability, and I think people just aren't aware of it. So I'm trying to advertise this theory to this community. This is a certain 40 n=2 gauge theory, which is dual to n D3 branes and 4 D7 braids and an orientifold. So this was first proposed by Sen in the 90s. Holography was worked out a couple years later by Maldacena, Ofer, and Fayazuddin. There was some very early work with integrability on the PP wave limit by Maldacena and on some kind of spin chain at one loop order. But I think people just forgot about this theory because there hasn't been any work on this theory in 20 years, basically. And so if people are getting bored working on n=4 ABJM and D1, D5, this is a completely new theory of which basically nothing has been done. So it's virgin territory. The symmetry, so it has an SO8 cross SU2 flavor symmetry as well as the R symmetry. The SO8 corresponds to the D7 branes, and the SU2 corresponds to the orientifold. And we have some partial results about this theory. So for instance, you can study open string scattering because you have these D7 branes. And so we computed the ADS Veneziano amplitude on the D7s in this paper. And so we have predictions for like the analog of the Konishi in that open string sector. So we have this 1 over lambda expansion. Currently, I'm working on the ADS Virasoro-Shapiro amplitude corresponding to closed strings with my grad student Daniela, who's here in the audience, as well as Pietro. And one very cool thing about this theory that it's much richer than the other theories you guys have studied, because you have both open strings and closed strings in the same theory. And so there's a hope that you can actually have some kind of open-closed duality, which is something we're also looking into, some kind of ADS-KLT related to what Maria was talking about. Yeah, and so the question is this theory integrable? I suspect it probably is, and I would claim this is the final frontier of IGST.
Well, let's thank the speaker. Why would it be the final frontier? I mean, is it like if we do this, then there's nothing else to do?
Well, as far as I know, there is no other example of ADS-CFT, which is not just a deformation of the known examples.
Right.
Yeah. So, I mean, if you could tell me another example of ADS-CFT which has a weak string coupling limit, I'd be all ears. But I'm pretty sure there is none. I mean, because in 4D, you can classify all n equals 2 Lagrangians, and there just aren't any. So this is the only theory. I mean, there's like trivial variations of it where like you add an orbifold or something like that. But it's the only truly independent theory in 4D. And in 3D, you also don't have any other examples. Because like the only type 2A example you really have is ABJM, as well as kind of like trivial generalizations of it. But but you don't have any like actually different theory in 3D, which would have a weak coupling limit. So yeah, so I think it's just this.
Okay, questions from the audience.
Thanks for your nice talk. I want to ask the function basis in ADS4, because I know in ADS5 and ADS3 the function is pure weight 3 functions. Yeah. And it's the same in ADS4.
It's the same in ADS4, yeah.
So in some sense they are maximal they have maximal supersymmetry.
I don't know if that's related to maximal supersymmetry. I mean, in ABJM you don't have maximal supersymmetry. You only have n equals 6. Okay. And also in ADS3, you also don't have maximal. You have half maximal.
Thanks.
Further questions? I'd have one. I recall, I think, Dorigoni talking about Dorigoni, Green, and Wang for the integrated correlator story. And they have an integral kind of formula where you have some integral over some parameter t, and it takes the form of some polynomial in the numerator divided by t minus 1 to some power. So is that related to your ansatz in the Mann somehow?
Wait, sorry. So the integrated correlator story is that you can relate some quantity you know from localization to an integral of the 4-point function. And so, indeed, that is used to check some of these results. Yeah, are you asking, like, do we have such a formula?
No, I was just wondering whether it comes down from your ansatz for the Mann transform, perhaps, that they had to find that somehow.
I don't think it's not related to the ansatz. I mean, like, the integrated correlator is like some exact thing. So it's a non-perturbative thing that you can relate, non-perturbatively a certain integral of a 4-point function to this non-perturbative localization quantity. You can then use it in a perturbative expansion to fix things. And so indeed, we use that, to fix the correlator to some order, and then we can use that to double check our results from, this ADS Virasoro-Shapiro. But yeah, as far as I know, that's the only connection.
Okay. Okay, so then we thank again and proceed to coffee, I guess. Right, so for the second session of this morning, let's welcome Julien, who will talk about bootstrapping thermal CFTs. And well, I see Ellie in the audience who is on the list of authors, and she said all Hamburg came, so I guess there's more of you. So let's see this.
Should I wait still, maybe? I think like a lot of people are still missing, no?
We do another 5 minutes, like first time around? Well, the boss is not here.
I have the feeling, or maybe they ran away from my talk, but...
So this is Gong from the Gong-Show. Somebody said it's a real gong.
Oh, really?
Well, I guess you should get started. They will be discussing something terribly important. And it's an invitation to chat, but because it's all... Yeah, right. Okay, so let's get started on bootstrapping the thermal CFTs. Then.
Is the microphone on? Good, good. All right, then thank you for the introduction, and thank you to the organizer for putting together such a nice conference, and for giving me a chance to talk about this work here. So I will be talking mostly about this paper here, which was done with my collaborators here, and in particular, Ellie and Dennis are here in the audience, so if you want to ask them a question, feel free to ask them. So this is going to be the outline of my talk. I will start with a review on CFTs at finite temperature, as I'm assuming that many of you might not be familiar or so familiar with this kind of setup. Then the second part will be on bootstrapping this system. So if you want, this will be the climax of the talk. And then I will show some application, in particular for holographic theories, which I hope will be interesting for a big part of this audience, and conclude with some future direction that I find interesting. So let's start with the first part. And I want to give you some motivation for studying CFTs at finite temperature. The first thing I would like to say is that temperature is unavoidable in experiments. And one interesting and important theoretical question is if you start with at a critical point at 0 temperature and you turn on the temperature, what happens along this line here? That's where the thermal CFT lives. Another interesting aspect of thermal CFTs is that in the context of holography, they are dual to ADS black holes, so it gives you a way to study those interesting gravitational geometries. Right. I mean, so I'm thinking now of a condensed matter type of thing. So if you... All right.
So like for instance, if you have the icy model, you get to the fixed point by tuning the temperature. If you go away from the fixed point, that's not related to going to S1. Like that's just related to changing the coefficient of Lagrangian and the mass and the back and forth.
So, okay, maybe we can discuss that later to not go into details here, but yeah. Anyway, let's start with something simpler anyway than this, which is how to go from CFT at 0 temperature to finite temperature. And one way to do it is, as you were mentioning, to change the geometry. So on the left, you have CFT on a flat space here, and you can compactify the time direction, and it turns into this cylinder geometry on the right. So here you have a circle of circumference beta, which is the inverse temperature, and this scale breaks the conformal symmetry. And in this setup, you can study correlation function, and in particular, 2-point functions will be the focus of this talk here. So let's see how this affects the kinematics. And I prepare a table that compares 0 temperature and finite temperature cases to compare, to give some intuition. So at 0 temperature, a 2-point function is kinematically fixed to take this form here. But at finite temperature, it's not constrained and is a function of 2 variables, at least not directly. Then on the side of the OPE, the radius of convergence is finite in this geometry, so the OPE does not converge everywhere. It's important. And then on the side of the CFT data, while at 0 temperature you have the scaling dimensions and the 0 temperature 3-point function, at finite temperature you have those new coefficients here, B's, which are related to 1-point function in the thermal background. So here you have a 1-point function, and the residual symmetry fixes those 1-point function to take this shape here. And in particular, you have 1 open coefficient pair operators. So those are the new unknowns of the system here. And one thing that I would like to emphasize is that the spectrum stays the same even when you change the geometry. That's important for our applications. So to treat this dynamical information, we will focus on 2 configurations. One will be the 2-point function that I showed before in full generality. And one will be a simpler configuration where the 2 operators are aligned in the same thermal circle. So I will refer to those 2 configurations as normal and easy. This might not be the best way to describe them, because actually normal is not much harder than easy. And easy is not that easy, actually. So, but this will do for today, right? So if we start on the left side, you can do a block expansion of this correlator within, if you're inside the radius of convergence. So those F here, I will not enter into detail, but they are like conformal blocks at finite temperature. And the A's, they are thermal OPE coefficients, which are related to the coefficient of the table before in this way. They are product of 3-point functions at 0 temperature and 1-point function at finite temperature. So those A's will really be the goal of our bootstrap framework. What we want is to constrain these OPE coefficients. So now on the easy side, what happens is that this expansion simplifies a lot, and you have an expansion in powers of tau over beta, where now those coefficients here, the A delta, they are linear combinations of the AO on the left. So what you lose is the spin, the resolution with the spin here, this letter J. You have only delta here, and those are degenerate. But another advantage, which is very important, is that DOP converges everywhere here because you're always inside the good region. So this setup, while being easier, it still captures most of the physics. So I will talk about both setups, but often it's good to start with this to explain some physics, and then go to the normal case. So now I would like to present you the bootstrap constraint that we will use, and it's basically periodicity. So the idea is that if you have, at least for scalars, if you have two operators on the cylinder and one operator makes a full circle, you come back to the same configuration. So this is this constraint here. But if you include parity, one nice way to see, to rewrite this equation is this one here. And to make my point, let me set beta equal 1 from now on. This will be the case for the rest of this talk. And now you can see that this really looks like a crossing equation of the type we know and love. So here you can see this as having two channels, one S channel where you want to expand around tau equals 0, and one T channel where you want to expand around the tau equal 1. And the DOPE that we saw before is not periodic. So what we want to do is to use the constraint from OPE, use the constraint from periodicity to obtain strong constraints on the correlators. To give some intuition, let me conclude this section with an example of GFF. Hopefully this will make everything more concrete for everybody. So generalized free fields, they satisfy this equation of motion. And you can calculate the correlator analytically or exactly. And what I want you to see in this expression here is that this is basically a zero temperature propagator that you shift by this m beta, and then you sum over all the possible shifts, or over all the possible images. And the reason why I insist about this method of images is that it's something that will come back throughout this talk in various ways. So it's good to have seen it in a simple example, I think. This sum cannot be performed in general, even for free theory. But if you go to the easy setup, you can perform it, and you see those Horowitz zeta function appearing. So those are nice functions. If you've never seen them, there's nothing to be afraid of. They're really nice. And the reason I show them to you is because later on in the talk, even for interacting case, they will be the building blocks of our correlators. So my hope is that later, when the Horowitz zeta comes back, you have this warm feeling inside that you're like, this was free theory, it's simple, we're happy. I hope it happens. But to try to enforce this feeling to happen, let me set delta phi equal 1 and show you that those are really very simple trigonometric function, for example, this one. Right? Now, if you look at this in a plot to gain even more intuition, the pink curve here is the usual zero temperature two-point function with this typical decay, while the green curve is the finite temperature correlator. And the periodicity here shows up in two ways. So one is through this mirroring structure from both sides that you can see. And the other one is that here, if you go beyond 1 and go to the next images, so to say, you should see the curve repeating again and again and again. All right, I hope that this brought a little bit of intuition around the kind of system that we want to study. Let me now move to the bootstrap. And here in vague terms, the spirit will be to use the spectrum as an input. And what we would like is that if you give us a spectrum, we are able to give you back the thermal OPE coefficient. So I hope for integrability people that this stimulates your imagination and that you can come to us with your favorite theories. And let me start this section by looking at the easy case, where the two operators are aligned on the same circle. So our goal here will be to derive a formula for this correlator that encodes the analytic structure that is manifestly periodic and that contains the OPE coefficient. So to do that, we start with the analytic structure, which takes this form. So here we're in the complex time plane. And if you look on the real axis, you have all those poles that corresponds to the operators always colliding once you make a circle. And they can have branch cuts that extends in this way. So once you have this structure, you can use a Cauchy's integral formula and deform the contour to obtain a dispersion relation of this type. So the correlator here is equal to this first term here, where we drop the arcs, and we pack them into the second term here. What we like about this kind of formula is that it relates the correlator to its own discontinuity, and this is often a simpler object to deal with. Another good thing about this formula is that it is periodic, and this we enforce by summing over all the possible cuts. And one final word about this is that I will not enter into details, but one can show that the arcs are actually given by a constant, which we will refer to as kappa. So now we have this nice formula here, and the only thing that is missing from the goal of the slide before is to use the OPE, to have the OPE manifestly in this formula. So to do that, we insert the OPE in this correlator and resum, and we see the Ovid zeta appearing at this point. And you know, because you've been attentive, that this is the the GFF correlator that we saw before. So now we have a super nice formula that says that any thermal correlator can be expanded into a GFF correlator up to a constant that corresponds to the arcs that we dropped. So if we think of the list of goals that I gave before, the analytic structure is inside because that was our starting point. Periodicity is inside because we summed over all the images. And the OPE is now inside. The OPE coefficients are here still unfixed. So let me now revisit the GFF example and show how this formula can be applied there, and hopefully to convince you that this is a powerful tool. So this is the formula that we just derived in the previous slide. And the spectrum for GFF is given by the identity and the double twist operator, where those operators are given by those scaling dimensions here. But if you input the spectrum in the formula at the top, what you will find is that those GFF correlator, they hold 0 when this argument is negative for integer delta, so unless they have anomalous dimension. And this immediately kills the double twist spectrum from this formula. So we get our final result, which is the one that we had before, is that it's simply given by the identity from this formula, the GFF correlator. And let me emphasize that the double twist operator, it's not that they are not present. They are there. If you do a block expansion of this correlator, you will find the double twist spectrum. But from this formula, only the identity is needed to reconstruct everything. So that's the lesson of this example of GFF, is that the double twist operators, they can be reconstructed from the identity. So that shows you how you need a very small part of the spectrum really to solve the problem. Later, I will show how to apply this in interacting theory. But before that, let me quickly discuss the normal case where the spatial separation is reintroduced. So in some sense, you can do exactly the same step as before. You can derive a dispersion relation. Here it's in different variables, but you can see those as conformal cross ratios. You have a kernel here, but this is known. This can be derived, and it's not very complicated. It's periodic as before, because you sum over all the possible images again. And the arcs can be shown again to be simply a constant. Now, if you insert DOP, what you arrive to is a formula of this type, where here you have a sum over images of the conformal blocks. So it's a bit less elegant than the Ovid-zeta formulation, but in essence, is really the same type of formula. And it satisfies the same things that we wanted to have previously. Okay, so let me move to applications and hopefully make this whole framework more concrete for everybody. I will start by a simple example, which is the ON model in the context of the epsilon expansion. So here is a review of the ON model. So you can start with this action here and take it to the fixed point. And our goal will be to bootstrap the correlator of fundamental fields. So this is this one here, which has this dimension here for the low epsilon order. So in the case of the easy setup, we use our formula, our expansion in GFF correlator. And here we simply want to input the spectrum. So at order epsilon, the spectrum, just by normal counting, can be determined to be the identity and those double twist operators. So the identity is free theory, and I'm going to look only at the interacting part, so we can throw it away for now. And then we saw before that from the double twist spectrum, nothing will contribute to this formula unless the operators acquire anomalous dimension. And in fact, one can show that only the lowest spin of this family will receive an anomalous contribution at this order, and this is the operator phi square, while the family here will not contribute at all. So this is a huge simplification. Again, they will re-emerge as OPE coefficients once you re-expand your result, but they do not contribute in this formula. So the final result for this configuration is this one, which you can write in this form here. And the only things that are left unfixed is the free theory finite temperature OPE coefficient for phi square. So that is known. And the anomalous dimension for phi square. So this is 0 temperature input for us and is also known. So at this point, you already fixed the full correlator. And you can do this also in general for the other configuration, and you get something very similar. And we checked for sanities that this matches the corresponding Feynman diagrams. So this was a simple example, but just to see how the framework works. And now I would like to show some work in progress about 4D holographic theories, where the result is actually not known. So those are new results that should be interesting. So there's been a long-standing problem on this case, which is to determine this two-point function of scalars at strong coupling, so in the really pure holographic regime, for integer delta phi. So for instance, that includes the case of n equal 4. And you can have this kind of picture in mind. So you have your boundary theory here with the two operators. And there is a propagator that we want to determine that is made non-trivial because of the black hole backgrounds here. And the obstacles to calculate this are the following. So even if you go in the large n limit, any multi-trace operator can in principle contribute once you turn on the temperature. You can determine this really by n counting. And that's, of course, a complication. And for this case here, the spectrum is the following. So you will have the identity as always. You will have double trace operators. They are analogous to the double twist before. But now you have also multi-stress tensor operators, which you can view as the gravitons that really make this propagator a non-trivial one. And additionally to this obstacle, we have another one, which is that So you can determine the low-lying OPE coefficient for the stress tensor sector. And what you find is that they have poles for integer delta phi. So here's an example of one. You can see that here, if you set delta phi equal 2, you have a problem. And what this means is that for integer delta phi, those poles, they have to be cancelled by contributions that come from the double trace sector. So in that way, they will be made finite. But the double trace sector, so far, there has been no way of extracting these coefficients. So this was an open problem on how to recreate this correlator fully for integer delta phi. But this degeneracies, the fact that the operators mix in this way, for analytic bootstrap, this is actually quite an advantage, because you will never see those poles. You will always see the combination of the OPE coefficient, and you will always be, have a simpler formulation of this problem. So to illustrate this more precisely, consider again this easy configuration. And we take our expansion into GFF correlators. So this sum now is over the operators is finite. And in fact, as we saw before, double trace or double twist do not contribute unless they have anomalous dimension, which is not the case here. So only the multi-stress tensor coefficient appear here. So if you want, we are circumventing the problem of the poles by considering only the ones which are not degenerate, and those are the ones which do not have poles. So immediately from this formula, we are getting the correlator in this limit for arbitrary delta phi integer. And this is how it looks like for the first terms. So it has quite a nice expansion as well. So there is still this kappa to fix. Hopefully we can fix it. And before I conclude on this, let me mention that the bootstrap for the other configuration is still a work in progress, because here the arcs are not trivial, but I hope we are able to do it as well. But already this correlator is a new result that was not obtained before with other methods. Okay, so let me conclude on this and discuss, take the remaining minutes that I have to discuss some future directions that I find interesting. So one of them is to consider also a compact spatial geometry. So for instance, if you put the space on a sphere, this system is very interesting because it exhibits phase transition. So on the ADS side, you have a first order phase transition between the thermal phase and a black hole phase, which correspond on the CFT side to a confinement-deconfinement transition. So it would be fantastic to apply our tools to this setup and see if we are able to detect this phase transition through the two-point functions. Then another interesting direction is to consider defect operators, for instance, Polyakov loops, which are the other parameter of the phase transition we saw before. So we have shown in a previous work that in this setup, if you consider the correlators of either bulk or defect operators, the new open coefficients here are going to be the thermal one-point function for defect operators here compared to the rest. And one clear target for studying those is to study these correlators of defect operators here, where most of what I presented will translate into a one-to-one framework there. Then it would be great to do also some numerical bootstrap for theories where the spectrum is known to a great extent. So, of course, n equal 4, and also with or without Wilson line. And what we would like to do in this case is the following. So in previous work, we studied the ON model and produced this kind of plots. So you see each curve corresponds to a different n. And this is basically the free energy as a function of epsilon. And to create this kind of plot, those are the ingredients that were needed. We needed some rules, the knowledge of the low-lying spectrum, and understanding of the asymptotics. So for large delta, some approximation that would help us do this analysis. So now with this dispersion relation framework that I presented today, this provides an analytic control of the asymptotics. So this is good news for this kind of study. The sum rules are the same, they are universal, so, and they were derived by my collaborators in the past. And the low-lying spectrum, of course, has been studied by many people present here. And the dream would be to be able to produce this kind of plot for the free energy, but as a function of the coupling here. So really probe the non-perturbative regime for the free energy. There are more directions that we can consider. I will not talk about them now, but just in quick words. We can do fermions, we can do other theories that are interesting, go a bit away from criticality, work for the future. So that's it on my side. Thank you for your attention. And, let me know if you have questions. Yes, it's large n, yeah. Can you what, sorry?
Could you in principle compare it to some kind of supergravity calculation?
Yeah, I guess in principle, but I think so far the way people approach this is by solving the wave equation, and that happens to be not so easy to do. So there is a solution in momentum space in terms of Nekrasov-Shatashvili partition function. But then if you want to compare to this, you have to somehow Fourier transform it to position space. So what we are trying now to do is to solve this wave equation numerically and at least have this kind of comparison in some regime.
Yeah. Kolya?
Hi, could you give some comparison to what you do and this calculation of Joe and Simon on Hagedorn temperature, how they're like related, or what?
On which one? Sorry, which?
The Hagedorn temperature.
So how to? You mean how? So about this?
In the setups and what's the main difference?
So in the setup that I showed before, if you have only the finite temperature in the infinite space, you have only the black hole space, right? You don't have a phase transition. So to be able to probe this temperature, we would have to study this geometry here. I mean, I think, I don't know, many of what we do transpose to this, but I don't want to take too many risks in saying it's a bit unclear how you would probe the Hagedorn temperature from the two-point function. So I think there we have to do some conceptual understanding of what we are actually looking for in this two-point function to probe it. I don't know if that. Right. No, this is not a large N effect. It's really just the fact that if you take this expansion in GFF correlators, you always have this argument here, and it turns out that the Ovid zeta functions that I showed before, if this is integer and negative, this just goes to 0. So if you include quantum correlation, at some point the anomalous dimension kick in, and then this will not be true anymore. Then you will have this kind of, let me go back to the ON model because I think that's quite telling. You will have this kind of derivative with respect to that argument. So you need to look into favorable setups at this moment.
But I didn't really quite understand. The status is that you say you can construct this by that condition and then it contains the full information.
Yes. So by starting with this formula here, what this really highlights is that you need less information than if you would start with the block expansion. But still the information is there. It's just that you don't need to use it as an input.
So if you re-expand then...
so if you exactly. If you re-expand this now is in conformal blocks, all these operators will have non-zero P coefficients. Yes.
Okay. Yeah, question?
I have a question about the constant kappa.
Yes.
You know it explicitly, and on what does it depend, and is it important?
Yes, so I put it a little bit under the rug today, but in general, for me at least at this moment, the best way to have control of kappa is to consider this setup, where those have a special separation, and then you have more ways to fix this kappa. So for instance, you can request that at large distance, the correlator should decay in a certain way, so have a thermal mass or whatnot. And this will help you fix the kappa, since it's a constant that is always sticking there in whatever limit you take. So in general, you look around all the consistency conditions you have and you try to fix it. And this case is the most systematic way we have to fix it. In this other configuration, you have to be a bit more artistic about.
Yeah, Julius?
Question up here.
So, I mean, you can certainly consider correction. I'm not sure. I'm not sure at this point how they will, how it will play out. But yeah, I think you should expect them. Yeah.
Hi. So you're making this expansion of the correlator into GFF correlators. So is it correct to understand this as a kind of Polyakov bootstrap?
Yeah, I guess it is
like Polyakov
similarities, right.
Yeah, okay.
Arkady?
May not be a well-defined question, but suppose you're given free energy as a function of Toft coupling and temperature. If you differentiate over Toft coupling, from the general definition, it's the same as insertion of integrated action, which is integrated dilaton operator or dimension 4 operator. So is it possible then to relate expectation value of this one-point function to what you were talking about, if you know the free energy?
Right. So this is not something we have thought of so much, because we take the opposite approach, right? We try to extract the free energy from there. But it would be interesting to try and see if there's.
You're hopeful you can extract free energy, like.
Right.
Oh, okay.
But I guess the question is, if you would have this as an input, could you? Yeah. I think we don't know at this point, but that's an interesting question.
For free energy, it's known, you can compute leading term at strong coupling, sub-leading term at strong.
Right. I mean, in some sense, so the free energy is one of those coefficients here. It is the stress tensor one-point function, thermal one-point function.
Anything else? Let me just ask you, why is this so perfectly universal? I mean, do you expect if you really did something like this in N=4 some complex theory, you do also get the same structure?
You mean by structure, you mean this?
Yeah, I mean that you can...
Yeah, this. So we didn't rely on anything to, on few things. We relied to write this expression, but what you can do here is like, what I'm showing you is perturbative setup where this becomes integer, but it doesn't have to be, right? You could put the spectrum non-perturbatively and study this numerically. It becomes difficult, but
it does become.
But it's a universal expression in that sense, yes.
Okay. A very quick one about this kappa. In the holographic context, it looks like a global property of your black hole solution, right? It doesn't depend on your insertion points on the boundary. we know what the global properties of these black hole solutions are. So is this, that suggests it's some scheme-dependent thing?
No, I don't think so, because this is really, it's not going to be scheme-dependent. It's really part of this correlator here, and it can be related to an OPE coefficient. So I don't think it should be, I don't think it should be scheme-dependent.
It should be a function of the thermodynamic quantities of the black hole solution, for instance. You just don't know which one.
I think so, yeah. Yeah, I don't know. I don't know if I can comment super much on this connection, but yeah.
Thanks.
Do we have more questions? Another one. Just one more to proceed with the schedule.
Naive questions are the hardest.
Yeah, if I do, for example, the Matsubara summation of this string, what do I get? Do I get free energy partition function, something like that?
If you take the, sorry, say again what you want to do? To take the Matsubara sum?
Summation over the Matsubara frequency.
Of what?
Of G tau.
Of this here?
Yeah, I mean...
this is already the Matsubara sum, right?
Ah, this is already...
Like the sum is already inside, so this is the resummed...
okay.
Like, so the free theory has already a Matsubara sum inside. So.
Yeah, I think what I have in mind is to do the Fourier transformation for G tau and... okay, maybe just...
Well, yes, maybe one more, but we do need to get on.
In the 4D n = 4 example, when you have those multi-stress tensor and multi-trace operators that mix,
yes,
isn't there some like logarithmic contribution that actually contributes then to the these dispersion relations that then resolves this sort of mixing? Well, for us, we consider them as just mixing. We are agnostic about this, right? We're agnostic about what happens with the mixing, because this is the difficult part, and indeed, logarithmic contribution should be at least naively expected. That's what we would think looking at this. So instead, what we do is, because we have this formula here, we avoid this problem altogether, because the only thing we need to make this statement is the spectrum, and that we have. So when you do this, the ones that are mixed, they just don't appear, and they reemerge in this formula here. Thank you.
That doesn't answer directly your question, but at least that's how we deal with this problem. Yeah.
Okay, let us maybe clap again for the nice talk.
Is it working?
Yeah.
I guess, yeah, okay. Thanks.
Okay, so please let us know about constraints for conformal defects.
Okay. Thank you, and first I'd like to thank the organizers for inviting me and giving me the opportunity to give a talk. It's my first time in IGST, and it's been a lot of fun, at least so far. We'll see. Okay. Okay, yeah, the most of the talk will be based on collaboration with Amit and Deliang, but one of the examples that I'll cover in more detail will be based on work with Victor, Ben Deguz, and Jiexin. So yeah, okay, I don't think I need to convince people in this room that defects are important to study. They are kind of ubiquitous in physics. They appear across many physical systems. I guess the examples that people care about most in this room are Maldacena-Wilson line, for sure, but and also Wilson lines in ABJM. But I think in most rooms, probably this modified side, this impurity example is the most familiar one. Anyway, a p-dimensional defect breaks the conformal symmetry group when the defect is flat. It breaks the conformal symmetry group down to this conformal symmetry group on the defect and rotations around the defect, right? So The symmetry you'll see very manifest, the one that is easy to use, is the smaller symmetry group that you've broken things down to. But I'll try to explain today how you can still take advantage of the full conformal symmetry group. So let me jump to the main result first and then get into the details. So the main takeaway should be that if we look at this type of 4-point functions where we have two operators, these are defect operators inserted on the defect. So sorry, I should say this is specific to lines. We haven't worked out the higher dimensional case. Maybe I'll comment on that in the end. So this is now specific. We're specified to p equals 1. And in this case, if you take two generic defect operators inserted on the defect, OI and OJ, and you insert also two displacement operators, there are integrated correlator constraints on these type of functions. So these are 4-point functions. You multiply them by some kernel, you integrate, and there are some numbers that have to come out on the other side. These are the implications of the broken symmetry. So these were worked out in some way in Chern-Simon's theory before, but most of what I'll say today is based on our paper from this year. And I should mention that I think, maybe I should say it this way, the final kind of the main formulas that I'll present in a moment were also developed in I think conceptually slightly different derivation by another group. Well, Nadav is here. I don't think I saw Zivan, but you can ask them about this if you want. Okay. So these are the final results. So these Fs are, as before, just the 4-point functions depending on the cross ratio. And these kernels, we call them homogeneous because the right-hand side is 0. And there's a very simple polynomials that you multiply, integrate, and you have to get the result on the right-hand side. And another set are the inhomogeneous constraints. This is because you have something non-zero on the other side. So this is the spin representations of this operator O. And this delta O is of course, it's conformal, is SL2R dimensioned. And now the kernels are slightly more complicated. Sorry, yes, thank you. So lambda is the 2-point function of displacement. This is kind of the normalization of the displacement operator. It's an unambiguous quantity for defects. And typically easier to calculate than 4-point functions. So the reason it appears, of course, is because this F is canonically normalized. So if you insert two displacement operators and integrate them, you're going to get the canonically normalized 4-point function times the normalization. So before I jump into the derivation, this was tested, at least by us, in this set of examples. Okay. Yeah. Okay. I will get back to this in a moment. So there's been quite extensive tests of these constraints. Okay. Good. So let me explain the derivation. So I heard Shai talk to a master student on Zoom before, and he was explaining how to derive conformal identities for local operators, and I think it's good to review this. So we all know from the yellow book that, for example, that this identity in the first line should be satisfied for any local operators, and this becomes useful once we combine it with the second line, where we know the transformation of a local operator. This is just some conformal factor appearing. So we can try to do the same thing for lines. So let's say we have a line operator with some two insertions of operators on the line, and the first line is kind of the equivalent of the first line of the previous slide, and the second line should be the equivalent of the second line of the previous slide. Now here, a very non-trivial kind of piece of information is that we can remove this prime from W, from the Wilson line operator without paying any cost in terms of a conformal weight. The way to understand this is that any conformal transformation, kind of global conformal transformation, locally close to some portion of the Wilson line looks like a global rotation, translation, and some SL2R transformation. And an SL2R transformation, we know the line doesn't transform under. So this is, if you want, this is another definition of the fact that the defect is conformal. Good. So we arrive at this identity, but this identity in this form is not extremely useful, I guess. Not many of us try to write down correlators on curve defects. They also depend on infinite amount of information. And I wouldn't know how to use this, so this is why this says derivation component number 1. We need to combine that with another component, which is essentially irrelevant perturbation theory around the straight line. So any curved line expectation value with insertions or without insertions of operators, I can express in terms of straight line observables where I have more and more operators inserted. To second order, it's roughly just integrating the displacement operator twice. This V, which is the difference between the profile of the line on the left-hand side and the straight line profile, will be our kind of space-dependent irrelevant couplings, if you want. And good, there are also counter terms where there are more powers of V and other operators that can potentially have the right quantum numbers to appear. So in principle, this framework of irrelevant perturbation theory has, as you go to higher and higher orders, more and more kind of unknown Wilsonian coefficients that you need to, that introduce ambiguities. But now when we combine the two, so we combine the ability to expand both sides in this irrelevant perturbation theory together with this identity, which is a functional identity, right? It works for any profile V of the line. We can fix all of these irrelevant coefficients in this, all of these ambiguous coefficients in the irrelevant perturbation theory. So the point is that we gain kind of predictive ability to write down the expectation value of a line as we deform it. And this is not all we get from studying this identity. So also when we study to second order, we get all of these integral constraints, all of these integrated constraints that I wrote down before. Now, maybe I should point out this is a little bit like hitting a nail with a sledgehammer, in the sense that we have an infinite set of identities above. It's a huge set of identities, and we get only a finite set of identities in the end because we just expand this to second order. So in principle, this can be expanded to higher orders. This should include many more identities that should be satisfied for straight lines. But it becomes kind of algebraically more and more complicated to do this. So in Chern-Simons, we went to third order. In Chern-Simons coupled to matter, we went to third order, but there we already knew the 4-point function at that point. So it's kind of just testing that this framework works to the next order, but not really getting new constraints out of it. OK, so back to the tests and examples. I'm going to briefly explain 3, 5, and 6, maybe. I don't know, how much time do I have? 20 minutes. OK. Should have went slower. What? Sorry? Yes. OK, great. No, that's good news. OK. So first, maybe I should say why I won't review the n equals 4 example, which might be the most fitting for the room in a lot of detail. And the reason is that, in a sense, it was done before. So in n equals 4, the displacement and the tilt operator are in the same multiplet. And maybe I don't remember if I said it, but on the previous slide, I said that the constraints for tilt operators were already derived before we derived these constraints for displacement. And in principle, we were guaranteed to succeed as long as our derivation is correct. These constraints, kind of the cousins of these constraints, when you translate your displacement 4-point function into tilt 4-point function using supermultiplet, was tested before. So it's still a good test that the derivation is correct, but not maybe a new result in a full sense. Another example that maybe is familiar to the room is the 2D CFT that is dual to ADS3 times S3 times T4. So in this case, we have one parameter, which is the ratio between NS and S and RR flux. And we can study the kind of the defect that is dual to the stable string configuration in this background. One way to get the 4-point function of displacement is by studying fluctuations around this setup, and this 4-point function that you get satisfies these constraints. It's quite straightforward to test. But maybe one comment that I should make is that in this case, there is another way to try and get the 4-point function of displacement, which is a bootstrap approach where you have some general ansatz for the 4-point function and you try to fix it using fix the coefficients using supersymmetry and conformal symmetry. And in that case, you get everything fixed up to conformal symmetry of the defect. It's only on the defects SL2R. And in that case, you can fix everything up to two unknown coefficients. And if you plug this into the constraints that I presented before, you can fix one of these coefficients. So in a sense, it completes this bootstrap approach. The other coefficient you shouldn't expect to fix because it should be essentially the ratio of RR and NS flux, maybe renormalized in some way that you will not be able to fix. Good. Now I will review a bit in more detail the last example, also because I think this is a setup that hasn't really been studied before a lot. This is planar pure Young-Mills in ADS with a Wilson line on the boundary. Okay, so this is this is QFT in curved space, not a holographic setup. So first, let me say why we would care about such a thing. So if we start with planar pure Young-Mills in flat space and we take a probe quark and anti-quark or a Wilson line and anti-Wilson line or Wilson line going up and down in time far from each other, between them there will stretch a flux tube that it can be well approximated at low energies by effective string theory. Right? Now the fluctuations of this effective string can be studied using Nambu-Goto action plus corrections that incorporate curvature invariance and extrinsic curvature invariance. What kind of remarkable that was verified using lattice studies is that up to roughly QCD scale in 3 dimensions, this effective theory works pretty well. So you just need to tune a bit the Wilson coefficients, but there are no new degrees of freedom that you have to integrate in for the effective theory to continue working. And in 4D, roughly the same thing happens. You just need to add 1 degree of freedom, which is a pseudoscalar, a massive pseudoscalar, and people refer to as the worldsheet axion. And then, again, the effective theory works pretty well. So, yeah, maybe I should mention, since Shota, I think, said yesterday that I will mention it. I wasn't planning to mention it, but in principle, there are integrable theories that are close to both of these theories. So close is kind of a phenomenological statement here. But in 3D, there's an integrable theory just for the Goldstone scattering that is quite close, and in 4D is a theory where you have the massless Goldstones and also a massless pseudoscalar, which has roughly the same coupling as this massive axion, but is massless. Now, okay, so the question then to be asked is what more can we learn about this theory? And one of the hopes was that asymptotic freedom can tell us something about its high energy limit. But if you just study high energy scattering, for example, that has a lot of UV-IR mixing. So it's not something that you can easily isolate and compute using asymptotic freedom, for example. So our way of trying to cure this is by putting the theory directly inside the ADS space and curved space. So this setup has 2 limits. Okay, there's maybe a lot of information on the board, but we put the theory inside the ADS space with Neumann boundary conditions. With Neumann boundary conditions, general expectation in the community is that there is no deconfinement phase transition as you change the radius. This is unlike the Dirichlet boundary conditions, where at small radius you have a conserved current on the boundary, so you must have a deconfinement phase transition. And if I add these Wilson lines on the boundary, I have this funny situation where at large radius I have the confining string stretching between this kind of source and sink of flux. And as I take the radius to be smaller, as I cross roughly lambda 1 over lambda QCD, the ADS geometric confinement takes over. And the string is not even allowed to grow up to size 1 over lambda QCD because of the geometric confinement. So even if I put a non-confining gauge theory in ADS, I will get this kind of fluffy string in the beginning, but this line will just stay straight, this string width in units of radius of ADS. What happens in the confining theory is that at some point it starts becoming smaller in units of radius. good. So this is a setup that we would like very much to study because we have one limit, small radius, where we can compute things in perturbation theory and use the UV description of Young-Mills. And there's another limit in large radius where we have the effective string. And we would really like to combine, kind of understand how these degrees of freedom reorganize into those degrees of freedom. But unfortunately, computations in Young-Mills, sorry, maybe I should say. So one thing we would imagine plotting eventually down the line, at least on some qualitative level, is a plot like this, where we have the spectrum of one on one side, the other spectrum on the other side, and we try to understand how it evolves with the radius. This is in 4D. This is kind of how it should roughly look in 3D. So these are just impressionistic paintings. It's not any result. So you might hope to start doing computations using the perturbation theory, for example, but of course this is not so easy because these are Witten diagrams, and at least for me, it's very hard to do any computations with Witten diagrams. We managed to compute the 3-point function after some efforts. So we have OP coefficients of operators of this form, derivative, kind of perpendicular derivatives of f inserted on the line. But going any further than this was hard, like, for example, getting anomalous dimensions. So here come kind of these constraints that we had before. Let's try to use them in this case. So let's compute the 4-point function perturbatively and try to plug it into the constraints. For example, the homogeneous constraint that I presented in the beginning. And the first two give some O1 number that does not satisfy the constraint. We integrate them with this kernel, and we get something that is non-zero. That doesn't make sense, right? But it turns out that the reason for that is that the perturbative expansion does not commute with the integral appearing in the constraint. Okay, so if we are not allowed to first integrate the 4-point function and then plug it into the integral. We have to first integrate and then perturbatively expand kind of the result in terms of conformal data. And this can be done with some care. The reason for that is that this t to the n comes from the kernel itself. This t to the 4 minus delta you can imagine being some cartoon for the exchange of some operator. And once we integrate this, we get some number over an integer minus the dimension, and you can imagine that at weak coupling, dimension becomes integer, and you get a pole that goes like 1 over the anomalous dimension. I think maybe someone mentioned that already. The same thing happens in the bootstrapability papers, so maybe it's familiar to some of you. So once we do take this into account, we have this minus 5 over 3 that comes from the naive integration of the O1 part, and we have this, we call it enhanced part, where something from first order comes and contributes to the constraint already at O of 1. Something from O of g to the minus 2, something of O of g squared contributes already at O of 1. So we get this constraint, which allows us to determine some conformal data. If we do the same thing for the inhomogeneous equation, we can actually fix all of the conformal data. Lambda is the same lambda that Chai asked about before. It's a 2-point function of displacement, and we know it. I was just too lazy to plug in the value, but it's a free theory computation. It's very easy, this order. So you can do the similar analysis for the case where you have 2 generic operators and 2 displacement operators, and you get some annoying recursion relations that can be solved after a few hours of staring at them. And you get all of this conformal data just from the symmetry analysis of the problem, just from the broken symmetry analysis of the problem. So what's first thing you do when you get this, you look at these C's. This looks much simpler than the formula I had before here, but actually it matches exactly to that formula. So that's, if you want, that is the sense in which this is a test of the integrated constraints. So the fact that the perturbative computation of the 3-point function matches with this determination from symmetry. And then we have also a new prediction, which is the anomalous dimension, which is what we wanted from the beginning to be able to determine, and was very hard to do with Witten diagrams. So we are being, I guess, rewarded for looking at the symmetry more carefully in this case. So I think how much time? Sorry. 10 minutes. Oh, wow. No, okay. No, okay. I just, okay, I thought it would take me longer. But good. Maybe that means that a lot of people are confused, so some time for questions is good. But okay, let me then just say something about strong coupling. So At strong coupling, it's a bit harder to use these constraints to predict something. So first of all, we have an effective string action at strong coupling or large ADS radius. We can use the effective string description. This allows us to compute a 3-level 4-point function. Basically, it's exactly the same as in n equals 4 to this order, because there is in n equals 4 the scalars do not mix in this order, so we can are decoupled at this order. So it's really the same result to 3-level, and we might hope to be able to get one loop. So this is done using technology that was developed in this paper. Most papers, mostly in the paper by Forini and Bonomi, where we can use a dispersion relation based on the Lorentz inversion formula to compute, say, a regularized form of the 4-point function. From the regularized 4-point function, we can get the original 4-point function by adding some information about low-lying operators. So, okay, I don't want to review their work, but in principle, this is something that is understood in the literature and allows us to plug in the 3-level data and get the one-loop 4-point function up to some low-lying CFT data that is left unfixed. And this is perfect if you have a integrated constraint, right? Because you can just integrate the expression that you got and try to fix these unknown coefficients. And it turns out that at one loop, you can fix the displacement 4-point function up to one unknown parameter for this specific theory, this Young-Mills theory. Good. And you cannot hope to do better because there has to be some parameter that tells you in which dimensions you are. So actually, you can, everything I said, maybe I forgot to say, everything I said was for Young-Mills in 3D, the simplest setup you can imagine, Young-Mills in 3D ADS. But you can set up exactly the same setup in 4D, 5D, 6D ADS. And well, I guess you don't get confinement at some point, I think. But in 4D, you can do the same thing, and you should have exactly the same constraints on the 4-point function. The analysis is the same, so you better have one unfixed parameter that allows you to go between 3D and 4D, right? So one value will correspond to 3D, and another value will correspond to 4D. Okay, so let me just quickly summarize the results. So line defects, generic ones, satisfy a set of integral constraints that I presented. They are quite explicit. They were extensively tested. For ADS 3 times S3 times T4, we can use it to kind of complete the bootstrap determination of the 3-level scattering. And, 4-point function. And for pure Young-Mills in ADS, this allows us to determine a host of stuff, a bunch of conformal data. We hope that even this will help us go to higher orders in perturbation theory eventually by combining this with the dispersion relation coming from the inversion formula. Now, in terms of future directions, I think there are many of them. There are some that are quite straightforward, and the reason I say this is because I think we need to be motivated in order to pursue them. So, for example, higher dimensional defects, I at least don't know of many examples in the literature where we can get the 4-point function of displacement, so to test such a thing. So it's a bit, it would be very nice if there is a clear motivation for any of this direction, either higher dimensional defect or to include bulk operators, for example. That's also a straightforward generalization, or for interfaces of boundaries. In terms of directions where we are actively working on, they are here, and if any of you wants to ask me about any of them, feel free. I'm not going to say too much about them, I think, at this point. Maybe the first one is just that what I mentioned before, that in principle we have this identity that involves any shape of the line on the left-hand side and some other shape on the right-hand side. And we can expand both of them around the straight line. And at least I don't see how this does not encode a lot more symmetry, and I would like to understand the structure of this thing when expanded around the straight line in terms of the algebraic structure. Okay, maybe I'll stop here.
Questions to Mark? Yeah, Daniel?
Maybe the last thing on the motivations on improving path operators. Before we mentioned that when we differentiate with respect to the coupling constant, we have
what you can get, right, is some, okay, I don't know if I talked about this with you, I don't remember with who. So for a defect with no insertions and one bulk operator, in principle, this was worked in Marco's paper, Marco and others from 2016, where you can relate the 1-point function to the 2-point function with the displacement operator on the line. Beyond that, I don't think anything has been worked out. I don't know how that would help in the case that you are, so maybe this has some implication in the case you described. It's not immediate for me, but might be worth looking at, but I don't see any immediate. In principle, the reason that you would be maybe not immediately inclined to just sprinkle some bulk operators is just because then the kinematics become very complicated, right? But if you have some very specific system that you want to study, then you can probably use this type of, where you, yeah.
Can I ask something? I mean, in recent developments in the spectrum discussion in N=4, you get that, well, you kind of know that the perturbative expansion and recoupling determines the whole story because it's having like a finite radius of convergence. But then when you try to go to strong coupling, I mean, people have these trans series questions and then all sorts of things. I mean, as far as I understand, you say I do at 2 loops I have 2 V operators inserted, and at 3 loops there will be 3 and so on, and that's a recoupling expansion. But like for any theory, can I just naively apply this logics to a strong coupling expansion?
Sorry, so now we are, which context are we discussing? The Young-Mills context or the?
Yeah, I was just wondering, you had some comments on strong coupling. So okay. Do I think that the motivation that you gave at the beginning with these V operators for the identities you impose, is it valid or is it not valid?
Okay, sorry, let's, my comments about strong coupling, I think, were for Young-Mills, where it's strong coupling, we have a effective string description, and weak coupling, we have a perturbative description. I'm not saying one is valid all the way to the other. The hope is that there's some overlap in the validity region in the middle, and you can kind of extrapolate both or interpolate both. Say, have 2 or 3 orders from each side, and try to have some the 2-sided Paderi summation or something like this to just get some qualitative understanding of how the spectrum changes. In the context of the derivation here.
Yeah, right.
In the context of here I'm not assuming any weak coupling. If you want, I'm assuming, oh, you mean the V is weak, V is small.
Yeah, I mean, so that you get 2 V's for, so would the same thing apply at strong coupling? I mean, you just do effects with some inverse couplings or?
Okay, so maybe I should clarify here that V here is the coupling from the point of view of relevant perturbation theory, but this is the coupling here is how much you want to displace the line from the straight line. It can be a strongly coupled defect,
I get confused.
but it's no. So maybe I mean I did go too fast, so yeah, yeah. Okay. Right. So this it can be a strongly coupled defect. That's not a problem.
Right. Okay. Sorry about that. So is there some reasonable question?
Yes. Hi, Barak. I'm here.
Oh, hi. Yes.
So in the case of Young-Mills and like a flux tube in ADS, if you insert more letters, then you can construct like open spin chain. So is there any possibility of extracting reflection matrix of that open spin chain from your computation?
Okay, so you have to do a bit of translation to what you said. So if you insert, so what is the setup?
So the idea is that you insert more Fs at the same time at the same location.
But still on the
yes,
closed Wilson
yes.
loop. I insert many Fs. That perturbatively, it seems that we can determine. So what I determined so far is quantum numbers for a lot of derivatives on Fs. I can study operator with more F insertions, but I cannot fix all of the conformal data. It seems that I can fix everything up to maybe 1 number per number of Fs.
I see. So if you insert more Fs, then you can create an open spin chain.
Okay.
And then from there, I think like you might be able to, if you know the answer, you might be able to read off, for example, something like a reflection matrix.
So when you say the answer, you mean anomalous dimensions, for example?
Yeah.
I see. Okay, that's interesting. I think we can probably determine it perturbatively, to leading order in perturbation theory at least. So yeah, we can discuss this.
Anyone else? So if not, then let's thank Barak again.
But it wasn't crazy fast. I think. Yeah, I don't know. And always. Yeah, I guess you didn't say everything that was on your side. You didn't.
Yeah.
So
far enough. Talk to the, okay, here. Let's start. Okay, welcome back everybody. We have the last long talk of today, and then there will be a coffee break, and then there will be short talks for the Gong-Show session. So now for the last long talk, we have Nadav, who will tell us about rewarding defects.
Yes, so thank you to the organizers for inviting me. It's my third time, I believe, at IGST, but it's a special honor to be invited to this very prestigious university to speak here. And I will be talking about work in progress with my ex-PhD student Ziwen and my colleague here, Petra Kravchuk. And as you already heard before, there is overlap with the talk of Barak and his collaborators. I'm stupidly an optimist, so I will tell you about unpublished results, even though we were scooped. I hope nobody will decide to publish what they see in the slides before me, and especially you. For diversity purposes, I also have my title in Japanese. And just for this context, this is the Integrability Engaged in String Theory conference. My talk will not about be integrability, not about gauge theory, not about string theory. It will be valid for any arbitrary theory, but it can include also integrable theories. Now, in every one of these talks, we start by talking, so this is about defects. And as Barak did, we start with our favorite examples of defects. And then, as you all know, we specialize to have BPS Wilson lines and n equals 4 super Yang-Mills, except for today. Everything I'm talking about today is valid for absolutely every defect. You don't need supersymmetry. You don't need integrability. It can be a cosmic string as far as I'm concerned. And the defects break part of your space-time symmetry. So I assume that there is some space-time symmetry and possibly other global symmetry. And there could be supersymmetry if you want. And the defect will break some of them. And that was what is important. And just for notation, my defect will be p-dimensional and space-time will be d-dimensional. And as I said, if your defects are integrable, that is, don't feel bad. It works for them too. So every quantum field theory should have an energy momentum tensor. If you have a global symmetry, then you also have a current for it. If you have a supersymmetry, you will have a supercurrent. And they have very important correlation functions among themselves that capture things like central charges. In the case that you have defects, there are contact terms for these operators on the defects. So the conservation equation for the energy momentum tensor will get a contact term restricted to the defect in p dimensions. And the operator that it induces on the defect is what we call the displacement. For a flavor current, the operator we call the tilt. And if you want, you can give a name tiltino to the one for the supersymmetry, or displacementino. I will not talk about supersymmetry much. So these are operators that live on the defect. And again, some people are somehow fixated. So as an example, some people are fixated with Wilson loops in n equals 4 super Yang-Mills. So for their benefit, here is that Wilson loop, the Maldacena-Wilson loop. And the displacement take this explicit form, so it's a field strength plus something else, or one of the 5 other scalars that is not one of the scalar that is inserted in here. So these are the explicit operators. If you like this theory, this would be the example I am talking about. But you can also look at a non-integrable theory like the one Julian mentioned before, the Owen model, and say take the magnetic line, or you can take a surface defect or anything in that model. But for the magnetic line, it has this form. Phi is just a scalar. So you'd integrate the scalar, but there is no gauge invariance or something. So you just integrate the scalar, and then the displacement is W times the derivative of the scalar, and the tilt is just the other n-1 scalars that did not appear in your defect. And another definition is that you vary the defect W, so I still keep the name out of sentiment. You vary your defect with respect to its position in the transverse direction or with respect to its location in this internal space of couplings. And this is a formal definition of what the displacement and tilt are. And the question I want to answer are what are the consequences of the broken global symmetry on the defects, and they are going to be captured by correlation functions involving tilts and displacements. So here is the outline of my talk. You can look whether your favorite theory is mentioned here and when, and then you will know when to stop tick-tocking and start listening. So let's start with the simplest trivial identity. I copied these equations from before, and now we can integrate the energy momentum tensor to get a charge, for example, translation, P. And if you act with P on your defect, you will get an insertion of this, but because you're integrated, this insertion is integrated over the defect. And because of this delta function, it's only on the defect. And likewise with the tilts. So, and because this is a ward identity, the right-hand side should be 0 for now. So for any defect, if you insert a displacement and integrate, you get 0. And this is completely general, and it's a very trivial identity. In a way, it appeared already in this paper, and as Barak was also mentioning, in the context of bulk defect correlators, but this applies very generally. So this was for translations. If you have rotation symmetry, as we usually do before we put the defect, or if you have conformal symmetry, you will get this identity with other weights associated to the killing vector of this, or the conformal killing vector of that. So as examples, take as your starting point a defect with already 2 insertions in it. It doesn't matter what your defect is, I said. It doesn't need to be conformal. It doesn't need to be anything. It doesn't need to be a straight line. I will take it to be a straight line, say, with 2 extra insertions. What you get is that the integral of this defect with 3 insertions, when one of them is the displacement, has to be 0. And likewise with the tilt, and here I took 2, and here I took 3. It doesn't matter. So let's make it explicit and show you an application. So here I start with 3 tilts, correlation function of 3 tilts. I act with a global symmetry. I will get an integrated correlation function of 4 tilts, and that better be 0. Now, in this theory, 3-dimensional n equals 4 Chern-Simons matter theories, there are many such theories, and these people determined what would be the form of the correlation function, the 4-point functions of these tilt operators at strong coupling. And they found an answer that depends on 2 parameters that I call here eta and epsilon, changing a little bit their parameter. The tilts there, they have 2 that I write here as complex conjugates of each other. And so I take this relation, and I just integrate this function that they tell me is the answer. So they have a bunch of conditions that they wanted to impose, that they decompose into superconformal blocks, and so on. And you integrate it, and you find 8 pi squared eta. And that is equal to 0. So either 8 is 0 or pi is 0 or eta is 0. Let's go with the last option. And then you get that the answer is just what's written on the second line, which is the same answer as an ABJM. So when this was done in ABJM, there wasn't this extra parameter. They thought that they found they found an extra parameter, but actually there isn't any extra freedom. And I should say, I don't mean any bad for them. They didn't know about this identity. What they did is correct. I believe we just added something that they didn't know at the time of writing their paper. So the answer for N=4 theories and for ABJM is the same. Let me look at another case. So I start with 2 displacements and I add a third displacement that still should be 0. I told you if I integrate on one of the displacements. And now let me restrict to a CFT. In a CFT, the form of the 3-point function is completely determined. The dimension of the displacement is always 1 plus the dimension of the defect. So the 3-point function better be this way. And now I'm instructed to integrate this. And the integral of this, you would tell me, is going to be proportional to c. If I integrate over anything, because there is just a number here, they're a function. But you should actually be careful when you integrate anything that you need to know it also at coincident points, and at coincident points you may get delta functions. So here I'm brushing over it, and I'm telling you that actually the answer, the delta function cannot cure this, and the right-hand side really is non-zero. And there is an anomaly that Chris and collaborators found for boundaries and interfaces. It's related to the extrinsic curvature. And so the conclusion is that this equation that I told you about is wrong. And there is actually a right-hand side to it, which may be an anomaly. So all these equations, you need to analyze whether there are anomalies to them. And this is part of the reason that our paper is delayed, because we don't want to write only the naive equations. We want to include all possible anomalies in them. Let me give you another example. So take a tilt 3-point function and integrate one of them. And tilts have the dimension of the defect. So the 3-point function of tilts will have the usual form in a CFT, plus a possible contact term. And now I'm going to be completely honest. So if you integrate this, if I integrate tau 1, then in the vicinity of tau 2, I have here 1 over tau 1, 2, small distance to the power p. I integrate it over p dimensions. I'm going to get a log. And this log indicates that, that something is wrong with conformal theory. And this is how you would calculate the anomalous dimension of the tilt in conformal perturbation theory. So, but tilts are really exactly marginal operators. This is precise everywhere on the defect conformal manifold. So the conclusion is that D is equal to 0. And no contact term will help you eliminate this log. So that is absolutely true, except for one case where you have one-dimensional defects, and you're allowed this form in addition to this form. So here you have this taus that can change sign, and you have this symbol which has to be completely anti-symmetric. And that is an allowed, as far as we know, this has never been written, that this is an allowed form of marginal operators in oriented theory in 1 dimensions. And again, the right-hand, now you have again a contact term, but that still doesn't help you, and the right-hand side is not 0. And this example that Barak talked about in his talk, this paper that studied this model both via Bootstrap and via ADS-CFT, they actually calculated 3-point functions of tilts and 3-point functions of displacement and found that they are non-zero. This is not surprising because of the anomaly. This is a little bit more surprising because nobody knew that such 3-point functions are allowed. But they are allowed, but they are related to some anomaly, and then you try to calculate an anomaly polynomial to add to your effective action. And it turns out that when you solve the Wess-Zumino consistency condition, to all orders in the deformation of the, so W I take here to be a deformation of my line. So I try to think, I start with a straight line, but I deform it in any arbitrary way, and this is the allowed form to get, except that this is not good because this is singular at pi. And this actually indicates that this form should not really think of it as this way, and I should think about it as some kind of topological condition. So this defect is actually not a function of its position in this internal space, but it's some section of a bundle, and there is a global anomaly which has this cohomology of the loop group of SU2 with values and so on. Some slightly sophisticated math, but doesn't matter. And then you can calculate the cohomology, and you find an integrability condition that these parameters that appeared here that are somehow related to the number of brains in your, that induce this background is related to these integers with this fraction of pi. And we checked, and these numbers, as far as we see, satisfy this integral condition. The number of d brains exactly appears with this power of pi, so string theory seems to be correct. Yeah, so this is the flux quantization condition in string theory. So this is all I wanted to say about these trivial identities, and now I'm going to go to, which we still find nice results from them, and now I'll go to the more sophisticated identities, which also appeared in Barak's talk. So here you should think of me having two special operators arising from broken symmetries, any of the symmetries that are broken, and two other generic operators that can also be those, but can also be other ones. And the form of the identity is that I have a log, I have some polynomial of the cross ratios. Here I wrote it for two cross ratios, so generic, but it also works for dimension 1. And the right-hand side, you should think about it as having the commutator of these two charges that gave rise to these acting on one of these operators, and you get this two-point function. This two-point function of these changed operators. And this is the identity, and it's true for any of the broken symmetries. It's interesting only if they don't commute. And this gives you a relation between 4-point functions and 2-point functions. So here is an example in a 6-dimensional 2,0 theory with our surface operators. And this already appeared in my paper from a few years ago. And these people, including me, calculated the 4-point functions of tilts using ADS-CFT. And we found these 4 tensor structures, including this anti-symmetric one, and these D functions. And if you know what they are, that's good. And if you don't know what they are, you're better for it. And now you need to evaluate the integral, and you can just do the integral, and you find this structure. And this structure exactly is consistent with this commutator structure. It also is related to the curvature on S4. So it all works out very nicely. And then you can also do the same relation for other symmetries, the translations, rotations, and special conformal transformations. So in the same paper, we calculated the 4-point functions of the displacement, and you can look at it there, and it's just other different D functions. And you plug it into the equation, and it doesn't work because we had a typo, and then we're going to fix the typo, and then it's going to work. And then there is the other term, the last one term, which is this epsilon tensor, and that is again anti-symmetric, similar to the expression we had for the tilts in the 3-point function in the 2-dimensional theory, the ADS3 theory. and now it's related to some other cohomology. And this cohomology is also in the integers, and this is related to this coefficient of G, the number appearing here, 9 over 2n, is related to the form-from flux on S4, and that is quantized correctly, so M theory works as well, if you're worried. So how much time do I have? 10 minutes. Okay, plenty of time to go through the derivation. And the point of the derivation is that, well, the difficulty really is that everything here was defined to linear order. We defined the displacements and tilts by variating with respect to how far we move our line from being straight. And in order to go to higher orders in it, there are a bunch of ambiguities that are related to each other. You need to choose coordinates beyond linear order. You need to think of what is the second functional derivative at the same point, which is subtle. You need to act with a broken symmetry on a tilt or on the displacement, and that action is not well defined. Or you need to think of multiple OPEs of the same operators, which is again not uniquely defined. So you have a bunch of ambiguities, and you can choose a scheme to work very carefully in that scheme, in one coordinate system, one choice of OPEs, and so on. But what we chose instead is to work in a completely agnostic way, in a scheme-independent way. And here I have a version of this trivial identity. I just integrate over 1 tau 1 with a trivial measure, and that should be 0. But I added here every possible contact term when 2 points meet each other. In principle, you can also add higher contact terms where more points meet each other. And these things I pick up when this tau 1 hits these other points. I get an extra term. So actually, they arise from triple delta functions. And I get these extra terms. And all of these things are ambiguous and undefined. And I try to calculate them and find constraints among them. Or if I want, I can calculate them in any particular scheme where I define all these ambiguities that I have here. And in order to get this L2, which appears in this identity, I actually have to start at a lower order, starting with my defect, which is parameterized by this W profile, either in space-time or for the tilts, and act with a global symmetry e to the lambda. Lambda is a generator of my symmetry group that is broken, and I find a vector field associated to it. I work only to linear order in lambda, arbitrary order in W, and I find some relations between this W. This is the correct equation where this vector field acting on my partition function, on my observable, will be given by some anomaly. And I need to analyze all these terms, all these possible terms, and find all possibilities. Let me skip this slide, which tells you how to get L0 and L1, which it's pretty straightforward to find them in any reasonable scheme. You can also go to crazy schemes, but we don't do that. And then you find this condition on L2, that it's related to L1s, and L1s are determined. So this combination of L2s is actually scheme independent. So L2 itself is scheme dependent, but we find that a particular combination of it is scheme independent, and any time we can extract this term, we're good. So I remember as a young PhD student, you were always told that symmetries are important and they're the base, and we try to base everything on that, and global symmetries and gauge symmetries and so on. And I felt that what a waste that I'm not there when these things are discovered and all these symmetries are now very well understood. But I think that this is a case where we actually can say something new about how global symmetries act on a QFT. So I'm very excited about this. So just what we thought we knew about symmetries, they actually have very non-trivial identities when you have these defects that break global symmetries. And as I outlined, but I didn't say here, we have a very rigorous definition. We have to keep track of all contact terms, because when you integrate and you don't know what your delta function contributions are, it's meaningless. So you have to know what all correlation functions are as distributions, including all delta functions. And this is what is taking us time. And there are too many variations of these identities with all kinds of subtleties, and we haven't settled on a finite set yet that we want to publish in our first paper. But we will also have many of these plug-in formulas that you can take and apply to your favorite defect and check that your calculation is correct, or fix it, or fix extra parameters that are left free, like this eta that I illustrated at the beginning. So I could finish here, but a talk at IGST is never complete unless you talk about n equals 4 super Yang-Mills, or show these slides, or make fun of the main organizer. It's here, your phone is here. So these are the results from this paper of these distinguished colleagues. And this is another application of the integral identity. I should say that they found the integral identity completely independently of my student and I by just looking at the correlation functions and understanding it and seeing that they satisfy this identity. And they found another identity which is very particular to n equals 4. So it doesn't fall under this category. And as they showed in their paper from a few years ago, this is extremely powerful in the numerical bootstrap, including these integrated constraints. So this is another application of it. Then in a more recent paper, they looked at mixed correlators, and there for some reason they didn't guess the integral identities, and they didn't read my paper with my PhD student, Jake, who's up there. And then they would have known that there are integrated identities for mixed correlators as well, to arbitrary spin operators. As long as you have two tilts in them, you have the same kind of identities. And then a bunch of people calculated 4-point functions in n equals 4 super Yang-Mills at strong coupling, at large charge, all kinds of limits. Here is a subset of the authors. I don't like to shame people for having mistakes, unless those people are Nikolay or me. And we couldn't find any mistake in those papers. So even not, so Arkady, the reason for the mistake in our paper must be me. So everything works just perfectly with the tilts or with the displacements. So Barak had a slide where he flashed through this and said that everything works, and I do the same, except when you go to weak coupling, and there is a result from that same paper of people at some university. I don't know where they were at that time, where they look at this 4-point function at weak coupling and try to implement some version of this integral identity. And the prescription they tell you is to take the answer, include an extra term, and then take all logs and set them to 0. And this is not the way we teach QFT around here. And as far as I know, in QFT, you don't set log epsilon to 0. That's actually where the meat is. And the same issue arises also in the ON model when you do it in perturbation theory. And the resolution of this is that you need to include a contact term and treat the correlator as a distribution. And if you do that correctly, the log divergence goes away. And so despite their best effort, n equals 4 is still a correct theory. And it's well defined. And you don't need to do weird things like that. I should say, there is a logic to it. But the reason you could control it here is that you exactly know what is the offending operator and so on. And in other theories, you're not going to have this level of control, so you cannot really. It's a weak coupling feature, and it's a feature of all weakly coupled theories. It's a feature also of the ON model. But it's not, there is a way to do it legally, and when our paper is out, you will see that. So to conclude, there are many, many more examples to work out, and I'm working with Ziwen and Peter on it full time. But if you want to get involved and are interested in this, then talk to Peter or Ziwen and me, or you can hire Peter or me, but it will be much cheaper to hire Ziwen, who is applying for postdocs next year and soon for faculty jobs, and she is really the driving force behind this project. She was pushing it from the beginning and convincing us to work on it. Thank you. Thank you.
Question.
So in your earlier examples, you said that the contact terms won't save you, and so these coefficients must be 0. Can you also conclude then that there are no contact terms as well, or?
Oh, so in some, usually contact terms are ambiguous, and you can include them or you cannot include them, and there is nothing that that predetermines them. So you can just add contact terms to your correlation function. It will satisfy all the axioms of the CFT. We find, through these relations, you find constraints on the contact terms. So sometimes you will find that they have to be 0. Sometimes you find that they cannot be 0. Sometimes you find, as in this formula that I really flashed, and I don't expect you to have absorbed. So here we have contact terms, and we have these L2 terms, and I told you that they are scheme dependent, but there are combinations of them that are scheme independent. So here you have contact terms that are partially fixed and partially ambiguous. So, and this is the general rule, and I went way too quickly over this. Really, this whole thing deserves a whole course, not a lecture, but that's what I have. We can talk about particular examples if you have any in mind.
So there's a result for a 4-point functional displacement operator in n equal 2 theories that depends on a free parameter as much as in the n equal 4 Chern-Simons.
That's right.
Set that to 0 as well? And a related question is whether you have some holographic understanding of why that result in n equal 4 Chern-Simons equals the ABJM one.
So we have no holographic understanding, and this should be true for any theory. So I don't know all holographic duals of all n equals 4 theories. As far as the n equal 2 calculation, we are aware of it, and we haven't completed it. The form of the expression makes it a little bit harder for us to analyze, so we haven't completed it, and I don't know if we're going to do it in our first paper or not, but we're aware of it.
Are there other questions? I have one. So in the derivation of one of the identities, the question is, can you determine the full, all the terms in the relevant perturbation theory, all the couplings to all possible operators? Or do they have a simple, for example, we had a sum rule at some point, and we eliminated all these unknown couplings with another identity. Is there a way to really fix all of them?
I think it depends on a case-by-case basis, and I haven't looked at that particular part of your paper in great detail to say exactly that. As Barak already said, in the case of n equals 4, all the identities reduce to the same one as the identity for the tilt. In a surprising twist, for example, in ABJM, this is not the case. Even though ABJM has a lot of supersymmetry, one of the displacement identities is independent of the tilt identities. You can't get it by integrating by parts. It's still satisfied, and it's satisfied by the n equals 4 identity. Of course, the n equals 4, I wrote the expression for the tilt. You can do the same with the displacement. You're going to get the same. So all of them are satisfied once you set eta to 0. But whether these are independent or new or so on, it's actually better to work in a theory with no supersymmetry or a small amount of supersymmetry, then you have more identities.
Maybe you have already explained, but about the log epsilon term, you say the contact term can allow you to set it to 0 about the final slide.
Yeah.
How does it work?
How does it work? No, I didn't explain it. What I said was that here you get this integral that diverges. And actually, what you get is that the integral identity is not satisfied unless you add this extra term. And the way I would say it now is that there is another way to add this term in a way that will make this integral explicitly finite to begin with. So there is no log, there is no extra term to add. You just redefine things in a way that you define the correlation function as a distribution. So you know the value away from coincident points. You need to add contact terms, delta functions at coincident points. You need to treat it as a distribution such that in the way mathematicians define a distribution as integral against test functions and so on. And then for every test function, smooth enough and so on, you're not going to get any logarithmic divergences.
A different way to do this.
Sorry?
It's a different way to do this integral.
It's a different way to do this that is completely honest and has no ambiguities.
Thank you.
Another way of doing that is take G finite and take the limit and
That's right. If you can do a calculation at finite G, but again, in the ON model, you may not be able to do this.
Because this is equivalent to the Maldacena prescription for the Brent-Strahlung. Like he's putting a regulator, and then he's saying like there is 1 over epsilon. Who cares? So this is 0.
It's not a log epsilon. It's a 1 over epsilon.
Yeah, but it's a. I mean, like his power like this is log epsilon, but it's equivalent.
Oh no.
Come on, you can say like.
Oh no, we know that this is exactly the kind of thing that I don't want to be taught at King's College. Okay.
Oh.
We're in Bush House.
Yeah,
Bush House has different rules. Yeah.
So it's fine.
This is not how QFT works. Sorry. You don't cancel one log epsilon against another log epsilon. No. At finite G, that is perfectly fine. Finite epsilon, that makes no sense. But you can't do calculations at finite epsilon in ON.
Sorry, I'm talking about finite G, yes.
Okay. if you can do a calculation at finite g, there is no issue with the divergences. This formula is not at finite g. This is a perturbative formula. It's correct, don't worry. Makes no sense, but it's correct.
Other questions?
It's just minor things we're cleaning up, don't worry.
Okay, if not, then it's time for the coffee break. Let's thank Nadav again. And afterwards, we reconvene for the Gong-Show. Okay, thank you. Yes. Should I go there? Ah, it's okay. Okay, I can sit there. Don't worry. One minute, yeah. Someone?
Ah, yeah, I see.
Welcome back, everybody. So now we have the Gong-Show. We have 5 speakers. Each will give a 10 minutes talk, and after each we'll have time for questions. So first up is Nikolay Primi. He will tell us about a proposal for the ADS3 crosses 3 crosses 3 crosses 1 QSC.
Okay. Thanks, Andrea. And yes, I would like to present this novel proposal for a quantum spectral curve model based on some ongoing work I've been doing with Andrea himself, Ruven Frasek and Roberto Tateo. I should also mention that the local group at King's is also doing a similar thing, Kolya, Philip, Simon, and Ben. But you can ask about it later, maybe. So to be very brief, the quantum spectral curve is a method to compute the spectrum of planar ADS-CFT correspondences. And it's basically a Q system which is composed of two elements, the Q functions and the QQ relations. The Q functions are functions of one spectral parameter with some branch cuts, and that contain in their asymptotics the quantum numbers of the operators we wish to describe in the dual CFT. The QQ relations are functional relation between these Q functions, and their structure is determined by the global symmetry of the ADS-CFT models you're interested in. These are the quantum spectral curves that are so far known, with the relative symmetry and the symmetry of the Q system. We see some very familiar faces, such as n equals 4, ABJM, and also this ADS3 cross S3 cross T4 model. But today, I would like to propose a quantum spectral curve for this other ADS3 model, ADS3 cross S3 cross S3 cross S1, with pure Ramon-Ramon fluxes. This model exhibits integrability if 16 supercharges are exactly conserved, and this imposes some constraint on the geometry. This constraint can get resolved if you introduce a parameter alpha, which is basically related to the ratio of the radii of the two three spheres. And this free parameter is also contained in the symmetry group of this spacetime, which is two copies of the exceptional Lie algebra D21 alpha. Alpha is also contained between 0 and 1, by the way. So there is immediately an obstacle for a quantum spectral curve for this model, and this obstacle is that in the literature, the QQ relations are not known for this exceptional super Lie algebra D21 alpha. There is a way around it. You can consider a simpler model where alpha is equal to 1 over 2. This in the geometry means that the radii of the two three spheres are the same. And in this case, this exceptional super Lie algebra reduces to the more simple orthosymplectic OSP4/2. So the symmetry of this spacetime, when the radii of the two three spheres are the same, is two copies of OSP4/2, for which the QQ relations are already known in the literature, and they're also very similar to the ABJM Q system. So goal of this talk is to make a full quantum spectral curve proposal for this more symmetric case, but in the end I will also briefly propose some QQ relation for the more exceptional case D21 alpha, which as far as I know are not known in the literature. So let's start to describe this Q system for OSP4/2. We have two copies of them, but for now I'll only talk about one copy. We have 16 Q functions in it that can be grouped into these four families, P, Q, which are the most important ones, and these spinors and anti-spinors. The QQ relations for this Lie algebra can be derived from a simple set of correlations, which are these three matrix equations. The first two simply connect the P with the spinors and anti-spinors, while the last one lets you build these Q functions from the first three. This epsilon is just antisymmetric tensor. So in some sense, this Q is less fundamental than the others. You can determine it completely by all the other 12 P, Q, P, S, and S hat. Then we need two copies of this Q system, so we'll have a total of 32 Q functions. The one on the L wing will have the same notation I introduced right now. On the R wing, we'll just add a dot on top of the Q functions. Then, to fix the quantum spectral curve, we should impose some analytical structure on these Q functions. And the first thing you should do is to impose power-like asymptotics in both of these two wings. In particular, the P and P dot function will contain the SO4 labels of the operators in the dual CFT, so they will have integer asymptotics, basically. While the Q functions will have SL2 labels. So this will contain the anomalous dimension you're interested in computing in the end. And it will be, of course, non-integers. Finally, you have to impose some branch cut structure, and this is very similar to the other quantum spectral curve models. PMP dot will contain will have a single short branch cut on the real axis between -2h and 2h, where h is the 't Hooft coupling of the dual CFT. And Q dot will have a long branch cut on the real axis between -infinity and -2h, and between 2h and +infinity. However, this very simple analytical structure already gives some tension, creates some tension. In fact, if you start from the P function with this short branch cut and use the QQ relation, you can reconstruct the possible analytical structure of the Q functions. You get two different possibilities, one in which the Qs have a ladder of short branch cut in their upper half imaginary plane, and one in which they have a ladder of short branch cut in the lower imaginary plane. So how is this consistent with our assumption that the Q function have a long branch cut? Well, this is where gluing comes to the rescue. The idea is that you have these two possibilities, either this where with a long branch cut, or these two guys where there are a ladder of short branch cuts. If you have the long branch cut structure, you should be able to start in the upper half plane, find no branch cuts, cross here, and get to the lower half plane where there are still no branch cuts. And, but if you have this other analytical structure, the only way you can reproduce this is if you impose that you start in the upper half plane with this Q down arrow, which has only branch cuts here, and when you cross the real axis, you end up with this other analytical structure. This condition, which is basically just what happens when you analytically continue to the real axis, is encapsulated in what we call gluing. And for this ADS3 model, this gives also the opportunity to make these two different wings talk to each other. In particular, we should impose that if you start from this analytical structure and you cross this branch cut, you end up in the other wing and you find Q dot with this type of branch cuts. Opportunity reshuffled by some constant matrices, G or G hat, which are called the gluing matrices. So once you impose this, all the tension in the Q system is resolved, and you've basically completed your proposal for the quantum spectral curve. Then it's time to do some testings, and the main test we have performed so far, but it's still some work in progress, is the asymptotic Bethe ansatz limit. To do this, you should take L to infinity, where L is the length of the operators in the dual CFT. And in this case, the quantum spectral curve equations simplify enormously, and you can actually solve them exactly. From this limit, some Bethe equations emerge, and they should reduce to the asymptotic Bethe ansatz equations, which are known in the literature from the S-matrix bootstrap. We checked that they're actually the same, at least in some cases. By doing this, we also get some prediction for the dressing phases of the S-matrix here, which are still not fixed. In particular, the structure we seem to find is the following. These dressing phases are composed by a BAS phase, which is the same as n equals 4 super Yang-Mills, a piece which we call sigma extra, which was already found in the other ADS3 model and contains these famous logarithmic branch cuts, and a new piece. We do not have, unfortunately, yet an analytic expression for this sigma nu. We only know it's given in terms of a solution of a linear integral equation. But we also know it disappears for some very symmetric states, where in particular these spinors and anti-spinors Q functions are the same. Now, just in the last minute I'll briefly talk about an extension to the generic alpha case, and in particular I'll try to propose a Q system for this Lie algebra. Our ansatz is that the Q functions are the same as the OSP4/2K, so we still have these 4 families. However, what changes are the correlations. And as you see here, these alpha parameters enter the shifts that appear in these QQ relations. From this family of 3 equations, we can derive all the QQ relation and the Bethe ansatz equation, and the nice thing is that they actually reproduce what you should expect from a theoretical point of view. Furthermore, it's pretty easy to check that they reduce trivially to the OSP4/2Ks at alpha equals 1/2. Of course, there's still some open problems we need to address before finishing. The first thing we should do is to compute an analytic expression for this novel dressing phase sigma nu and check that it satisfies all the assumptions of a dressing phase, like unitarity and crossing. We should also extend our ABA limit, because what we did so far is only include the so-called massive modes, but this model also presents some massless modes, which we should try to include in the ABA limit. And finally, we should also try to do some numerical computation for this model to actually compute some spectrum. Unfortunately, this is probably harder than n equals 4 super Yang-Mills or ABJM theory due to the presence of logarithmic branch cuts, but I think tomorrow we'll hear something more about this for the other T4 model. And finally, we should also try to extend our construction to the full D21 alpha case, because so far we only have QQ relation and some basic analytical structure, but no gluing or other steps. Thank you for your attention.
Questions?
How do you include alpha, not 1/2? You mentioned this, but you didn't.
Yes. So basically, you choose alpha. Which there is alpha. And then the idea is that you still.
Can you use the microphone?
Sorry. The idea is that you should still assume the same analytical structure for the P function, and then using this Q correlation, you get this strange analytical structure for the Q functions. Where now the ladder of branch cuts is not evenly spaced, but the spacing depends by these alpha and alpha hat parameters. Another strange feature, it seems to me, that if you take alpha equal 1/2, this alpha hat is also equal to 1/2, so these two branch cuts will collapse on each other somehow. So there seems to be some non-trivial splitting of branch cut if you take generic alpha.
So does things simplify if you go to the alpha equals 0 limit, or alpha equal to 0 or alpha equal to 1? Do you get any sort of simplification? Or?
Well, there should be some connection with the other ADS3 model, because in this case, D21 alpha becomes PSU 2/2. But I don't think it's so trivial to see, because in that case, some of the connection in the Dinkin diagram actually break down. So I'm not sure what happens. It seems to be some sort of singular limit, actually, of this D21 alpha. While this alpha equals 1/2 is completely regular, even from the Lie algebra point of view. We should investigate.
There's a question from Volodya.
No, not really. Even in the literature, I don't think it's known. But also from the, yeah? Okay, thanks. Maybe we should investigate.
So how about the S matrix for the generic alpha?
Yes, so these papers I've cited here actually do the generic alpha case, but the dressing phase, it's not fixed. There's only a crossing equation written for it, but it's not solved.
So what's the dimension of this R matrix?
What, sorry?
S matrix dimension, local.
Well, it should be, but again, there's only a crossing equation in the literature. There's no explicit form, as far as I know.
Mm.
Other questions? That's one in the corner by David.
What about this new piece? You find is a complicated equation and not related with the previous version?
Yes, so at the moment we just have it in terms of a solution of some unknown nonlinear integral equation, which depends on the state you're describing. We don't know, since we don't have an analytic solution for this, we don't even know if it's unitary or it satisfies some crossing equation. To do it, we should solve it and find an analytic expression for it, but still work in progress, let's say.
A question there.
So what does it mean that the phase is BS times extra times nu? I mean, you could have said it's new. Are you just taking out the branch cuts? I mean, why do you say the phase if there's an unknown piece? A piece is BS times extra times nu. I mean, you could have said it's new. You're taking out the branch cuts, so what do you do with it?
Sorry, I didn't understand the question. Right, of course. But, well...
What's the logic? I mean...
If you take these special states, it's not really new. These two parts are already inside this other ADS3 model. So it's not really new. The only new piece is this one, sigma nu. The rest you find already in some other models, which should be related to this in some sense, because, well, they're connected by some compactification, basically, on the string theory side. But yeah, I agree. the full object is new, like the full phase is new.
Yeah, okay, it's time to change to the next talk. So let's thank Nikolay again.
Don't start me yet.
No, I won't start the clock yet. Okay, and next we have Julius, who will tell us how to go from glue balls to massive strings.
Thanks very much. Thanks to the organizers for giving me this opportunity. Today I'll tell you about work done over the past 2 to 3 years, mainly with Nika, who's at King's. All right, so let me start. I like to start talks with this question, which is, what does it mean to solve a quantum field theory? I mean, I know this audience doesn't need motivation, but just in case. Right, so in order to solve a quantum field theory, you need to know all correlation functions. In general, this is quite hard, but if you have a conformal field theory, then it becomes slightly easier because you just need to solve all 2 and 3 point functions. These 2 and 3 point functions together are called the CFT data of a conformal field theory. The 2 point functions are called the spectrum. 3 point functions are characterized by numbers called structure constants or OPE coefficients. So then the next question you can ask is, suppose there is some quantum field theory whose spectrum I know. Can I take the knowledge of the spectrum, add into it constraints from crossing symmetry and some constraints from holography, and use this to extract OPE coefficients? That's the question I like to ask in my research, and I want to tell you a bit more about some progress that we've made in this direction. Right. Okay, so again, this slide is probably not needed for this audience, but n equals 4 super Yang-Mills is the theory that we're going to look at. In particular, we consider the planar limit, where we take the Yang-Mills coupling to 0, the number of colors to infinity, in such a way that the 't Hooft coupling is kept fixed. The reason we consider this limit is because the integrability of the theory, this theory becomes integrable in this limit, and also the only states that we need to consider are single trace states. Single trace states are just traces of L objects, and these L objects are made up of your favorite number of covariant derivatives acting on your favorite combinations of fields in the n equals 4 Lagrangian. Operators in the theory are labeled, therefore, by the bosonic symmetries they have. The bosonic symmetries of n equals 4 super Yang-Mills is the 4D conformal group times 6 SO6 R symmetry group. So in general, you have 6 unique labels that define a single trace state. These 3 labels refer to the SO6 R charges, and these 3 labels label your 4-dimensional conformal group. Representation, the representation under the conformal group. And out of these 6 labels, 5 are integers or half integers, and the dimension in general could be a non-trivial function of the 't Hooft coupling, of the parameter of the theory. And in general, if you want to solve the spectral problem of this theory, you want to understand the dimension for any value of the 't Hooft coupling. What you can then do okay, so the dimension is what we want to study, and we want to study operators or single trace states in this theory in the limit of large 't Hooft coupling. So in the limit of large or strong 't Hooft coupling, the operators in this theory can be characterized in the following way. So instead of measuring the dimension of an operator, you can measure the eigenvalue of its quadratic Casimir. It contains other things, but also contains spectral information. And this object, you can expand its strong coupling, and it will have an expansion like this. It has some expansion in powers of 1 over square root of lambda, with the first coefficient in front, a number which I like to call delta, which corresponds to the string mass level. And this is because single trace states at strong coupling are dual to massive strings. So that's how you can actually see this relation. The planar spectrum of the theory is solved, a long journey which was pioneered by various members of this community, and my favorite way of doing it, at least, is called the quantum spectral curve, and here's the spectrum of the theory. So 2 years ago with our collaborators, we got these plots. we got these plots, and I have 5 minutes left, okay. And you can look at these plots, and you can see that we have all states in n equals 4 super Yang-Mills below some bare dimension. That's not the focus of this talk. The focus of this talk is to look at what happens to these states as you go towards strong coupling. As you go towards strong coupling, you can already see that the states band according to the string mass level in the following way. So there's an overall envelope with 2 times square root of some mass level times lambda to the 1/4. That's the first thing to observe. The second thing to observe is that the spectrum itself organizes into Kaluza-Klein towers. And the reason that happens is because as you're going to strong coupling, in a holographic picture, you're probing the flat space limit, so you expect the formation of these towers, and we see both of these things. So now that we have the spectrum, the next thing to ask is how do I extract OP coefficients from this? So just before we do that, let me give you a bit more paperwork about the spectrum at strong coupling. Yeah, that's fine, thank you. Paperwork about the spectral data at strong coupling. So as I said, we are probing the flat space limit. Massive strings organize themselves into Regge trajectories. They look like this. So you can do a Regge trajectory delta string mass level versus spin. And basically, at each value of delta and L, there will be some operators that you exchange, some massive strings. Most of the research in this community has been focused on the leading Regge trajectory, and that's because the leading Regge trajectory is non-degenerate. So whatever Maria was telling you about, whatever Benjamin was telling you about, Alessandro, all of this is on the leading trajectory. I like the sub-leading trajectories. The reason I like them is because for a given vertex here, for a given value of delta and L, you have not necessarily a single operator. And the question that Nika and I tried to ask is spectral information plus constraints enough to extract real information about these? Turns out the answer is yes, and in order to see that, we have to play a game which starts by the work of various people at Oxford over the past few years. So as we heard in the morning, these various people, what they've been doing is computing some string amplitudes in the flat space limit of ADS and systematically computing curvature corrections to it. The point, from our point of view, is that every time they compute a curvature correction, they get some constraints on OP data. So you can focus on some OP coefficients, expand them in a nice way in terms of some numbers here. And essentially, every time Fernando and friends solve a new order, the next curvature correction away from flat space, they get some constraints on these Fs and Js. Js, as I showed you in the first slide, characterize the dimension. Fs characterize OP coefficient. Okay, so that's the setup. And now I'll show you some results and stop once I've shown you the results. Right, so the first thing we did was we considered 4-point functions like this, where you have 2 gravitons and 2 KK modes. In that case, again, we studied states in the sub-leading trajectories, and we saw that there is actually quite high degeneracy. So this point has degeneracy 3, this point has degeneracy 7, this point has degeneracy 13. And what we wanted to do was input spectral data into constraints that you get for CFT data of these states and try to extract OP coefficients. So we did that. For all 3 cases that I described. I'll spare you the technical details, but the surprising thing is that we found that in all 3 cases, it seems that a majority of the OP coefficients seem to vanish at leading order, meaning most of the OP coefficients seem to be sub-leading to a minority of OP coefficients at strong coupling. So this was something very intriguing that Nika and I noticed 2 years ago, and then we tried to explore it a bit further. And we tried to explore it further by doing this. We said, okay, fine, let's not do Kaluza-Klein towers, let's instead study really the sub-leading Regge trajectories. Yeah, one sec. I have 1.5 minutes, that's great. Okay, so then we tried to play in the same game. We took constraints that Fernando and friends graciously computed for us, and we computed spectral data on our own. We made some assumptions based on, inspired by work done by Arkady and collaborators. And essentially, we tried to see if we can solve this system and unmix these OP coefficients on sub-leading Regge trajectories. We also had another piece of input. The other piece of input, again, I will spare you the technical details, but essentially, the other piece of input comes from the fact that if you actually stare at the subleading Regge trajectories, you will see that some Regge trajectories vanish at some point. But then you can always ask the question, what if I continue the Regge trajectories below the point that they vanish? And this gives you some more constraints on OP data. You can also construct what Andrea and friends call Regge bridges, which are an ingenious way of taking the subleading Regge trajectory onto the leading Regge trajectory and impose further constraints. Anyway, we do all of this, we fix a lot of parameters, and this is the result. It's, again, there's not really too much that you have to see here. The important caveat that I have to give you is that there are a lot of free parameters. We start with many free parameters, we end up with fewer free parameters. We fix them using slightly ad hoc assumptions. We get a result which has unsatisfactory from an integrability point of view matching to numerical data, but does have some matching. But the point, if you believe all of this, with all of these caveats, you will see that we see this vanishing of OP coefficients again. So it turns out, if you believe us and our assumptions, again, we are able to show that an infinite number of OP coefficients vanish on the subleading trajectories as well. So that's something interesting. And yeah, so I'll finish now with basically, my conclusion is the following, that yeah, it seems like there is some emergent selection rule at strong coupling. We've produced some evidence for it. We're in the process of producing more evidence. As Shai said, probably one should study in other theories as well. So we're trying to look at it in ABJM, maybe try to like string computations, etc., etc. So yeah, or also maybe we can use this technique as well. So yeah, that brings me to the end of what I wanted to say scientifically. The last thing I'd like to say is that roughly 20 years ago, this community started by a paper by Mann and Zarembo, and then yesterday I took this picture. So we're still at it 22 years later, and so yeah, so I hope, I wish everyone the best in their research. Thank you.
So I would like to ask, what would happen if you continue the spin to even lower, like lower than -2?
Yeah, we tried to do that, but our numerics was not, we were not careful enough with it. So I don't know the answer yet. I mean, we tried to do it, but we weren't very careful, and then we abandoned that. So, but it's something we need to explore. So.
Thanks.
Other question? By Benjamin.
I think I already asked you this question once, but I don't know if you made progress on it. So I was wondering if the zeros that you are finding could be explained directly by some computation in flat space string theory.
Yeah, that's the hope. We haven't made progress there. But you're right. In theory, one should just be able to construct the vertex operators directly and then see. And this is something that we should do, but we haven't done yet. It's something that we have in mind, but we haven't got down to doing that yet.
So what's the status in ABJM at the moment?
Well, okay, I mean, the status in ABJM is, again, it was hinted at by Shai. There are these Z parity odd operators, which one needs to try to understand, right? And if you want to play the same game in ABJM, then you can't, there's not just one type of long multiplet, there are up to 3, depending on whether you have even or odd spin. So yeah, right now, I think the status in ABJM is just to try to see if we can find these parity odd operators. We have some ideas about what they could be, but nothing concrete to say. But ideally, if we find that, if we find like a satisfactory way, I mean, if we find some operators which then at strong coupling match the predictions that they have, for example, then one could play this game.
So one needs this input from integrability to
Yeah, I mean, so there are two things to do in ABJM. One is just to find the operators that they predict that exist. And then once you've found them, then you can go to sub-leading in ABJM and try to play this game, which I spoke about today. So there are two things. We're still trying to do the first thing. So yeah, we don't have anything concrete there yet, but that's something we're thinking about.
If there are no other questions, let's thank Julius again. Chiara Paletta, who will tell us how to detect algebraic integrability of the deformed Rule 54 model.
So let me start by thanking the organizers for giving me the opportunity to present my work. Today I will discuss some ongoing work with Thomas Prosen in the University of Ljubljana. And the talk will be about the detection of algebraic integrability of deformed Rule 54 model. Since maybe those models are not familiar for the majority of you, let me start by introducing what are these rules. So imagine that you want to describe the dynamical evolution of some system, and you want to really find what is the possible simplest deterministic dynamic that you can think of. So let's look at this picture. In this picture, the time is going downwards, and this system is discrete in both space and time. This is the definition. The definition of a cellular automata is a system for which the evolution of one state only depends on the nearby cell of your system. Now, for this type of simple model, each cell can have two values, 0 or 1 or black and white. Now, we are interested in the evolution of this particular cell, and this one is in one state, and the dynamic given by this Rule 54 is the following. If at least one of the two states here is in the state black, then the cell that you are looking at will change state. So for example, let's look at this. We are starting from white. At least one of the two is black, so white will go into black. And you can look at all the others. So two white, the state does not change. If you have one black, it changes. And if you have two black, it also changes. There is a nice review of this model is given here. Now, this is really the simplest model you can think of, but surprisingly enough, a few years back, it was proven by Thomas Gomber, who is also in the audience, and Balázs Pozsgai, that this model is integrable, and furthermore is Yang-Baxter integrable. Now let me describe the dynamic of this model, and then I will move to the deformation that me and Thomas are looking at. So this model, the dynamic is given by one operator that is acting on even and odd side, so is periodic every 2 steps. And the rule that I was given, you can really imagine them as element in one matrix. Those are some transition rule. So let's take this model and let's add some deformation on top of them. In particular, Thomas introduced this deformation in 2021. He took the first state, so before in the undeformed model, if you have two white close, then nothing white goes into white. But now let's imagine that white can go into white or it can go into black with different probabilities alpha or beta. And also in this model, in this other rule, you have two white. Let's say that the black goes into black with transition gamma, or it can go into white with the rate delta. Then what he did was to naively count the conserved charges, and he observed that conserved charges were scaling linearly with the length of the system. And furthermore, he also used some numerical technique. For instance, he was looking at spectral level distribution, and he observed that even the quantum deformation shows some sign of integrability. So since I started in Ljubljana, what we try to do is to prove that this model is integrable, and even more, it's Jan-Baxter integrable. So this model is really like the simplest model you can think of. You start to add some quantum deformation, and surprisingly enough, you find that is integrable, but is Jan-Baxter integrable. So to show this, I will move into the technical part now, just to tell you that it's not very easy to detect algebraic integrability. So if someone would have come to me and show this model and put a bet, like, would you guess that this model is Jan-Baxter integrable, I will probably have bet no. But after some work, then we managed to show that Jan-Baxter integrability is also there. So my take-home message is that Jan-Baxter integrability is not as rare as we used to think. So let me now try to move into the proof. So one possible way that one can check integrability is the following. This matrix U is the matrix that has a matrix element given by this square that I was showing before. So one possible way is to check integrability is, can I identify this U operator as the Lax operator that is identifying my Jan-Baxter model? Now, to do that, there is a formalism that has been developed in these papers, where we all know that the definition of integrability is via this RLL relation, but we can also take one space and double it. So one way to detect integrability is to ask if you can associate the U, your dynamical evolution, with the Lax of the integrable model. But unfortunately for this model, this simple thing didn't work. But then we were thinking, is there still some hope that the model is Jan-Baxter integrable? And luckily there is. So to prove this, we really needed to use a different strategy. And the strategy was to notice that if you take the dynamical evolution of your system and you check which is the charge, the first non-trivial charge that commute with it, you will see that the first non-trivial charge has interaction range 6. And then now this range 6 charge is really the main protagonist of our proof, because what we did was to use the boost automorphism mechanism to show that this charge Q6 belongs to a tower of conserved charge of an integrable model. So the question on integrability can be brought into a different form, that is, does Q6 belong to a tower of conserved charges of an integrable model? And so this part is really, really technical, but you can think about this boost operator as really an operator that you apply to one of your charge and you construct the next conserved charge. And what happens for this model is that if you start from Q6, you can get the next charge commuting with it using the boost that has interaction range 10, and both of them now commute. And this is now a strong indication that the model is Jan-Baxter integrable. I want to be precise, like this is not really a proof, but it comes from an old conjecture that is called the star triangle hypothesis. It says that a sufficient condition for a model to be Jan-Baxter integrable is that the first two non-trivial charge commute and the second one is constructed from the boost operator. What we also did was to apply the boost again, and we got also the next conserved charge. I want to emphasize that now this is a charge acting on 14 sides, so if we didn't have the algebraic structure, then to get this charge you really would need to use a very powerful cluster. But then we got this charge, which we checked commutation, and then we also checked that it commutes with the dynamical evolution. And then we used this charge to construct the Lax operator perturbatively up to order U cube. Now this is a strong indication that also this model is Jan-Baxter integrable, but to have a complete proof of this, we would need to compute many more conserved charges and then resum. This was a method which was developed by, you can find information in this paper. It's called the Lifting Integrable Models by Anna and Marius, which are also in the audience. Unfortunately, for this model, this method does not really work because all the matrices that we are dealing with have these dimensions, so it starts to become very, very complicated. So let me emphasize that even if this model is very simple, Yang-Baxter integrability also appears here. Let me conclude. I was giving you a very strong perturbative evidence that a deformation of Rule 54 model is Yang-Baxter integrable. And something else that we are doing with Thomas is to take this model, so the deformation I showed is quantum, but you can also restrict it and make it stochastic, and we put some open boundary condition and we obtain an analytical expression for the NS. But again, the model is simple, but the expression of the NS in terms of matrix product operator involves metrics which have infinite dimensions. There are many other open questions. First of all will be to really prove that the model is integrable, so finding the full Lux operator. But then there are many things that we don't understand. For example, why the first non-trivial conserved charge has interaction range 6? Is there a way to understand this, not by brutally compute, but from just the expression of U? And then in this model, the transfer matrix that you can build, it commute with U, but somehow it does not generate U itself. So why is this happening? And then this is some discussion we are having if what happens in the open boundary condition in terms of the Scalianin algebra. And with this, I thank you for the attention.
Okay, maybe I wasn't paying enough attention, but why is it called Rule 54?
Thanks, yeah, for the question. Maybe, yeah, I didn't say it, so it's good to. So it's called the Rule 54 because if you look at this, so the first three are the same for all these possible rules. But then what changes is the output state. So if you start by reading from here, this is white. So 0, 1, 1, 0, 1, 1, 0, 0. You can take this number. This is in basis 2. But if you go to base 10, then you get Rule 54. Thank you.
Hi. So is there a way to detect kind of integrability experimentally by just modeling and checking some, I don't know, chaos, non-chaos?
Yeah, so I think Thomas got interested in this model especially for this, because if you compute level spacing distribution, he found Poisson statistics, so the model shows sign of empirically check of integrability.
Hi. So did people study also quantum deformation of other cellular automata models or not really?
Sorry, you are asking if
people study the quantum deformation of also other cellular automata models?
Yeah, so there is a letter, there is a project by Thomas where he was introducing this model and also the formation of another model. I don't want to say wrong because I cannot really remember if it was 201. So it was the same. Instead of F00, he was putting this 2x2 matrix. And then you can try to ask the same question if it's still integrable or not. But other than that, I'm not sure how much is done in terms of deformation. Yeah, it's something that we are thinking about, but we didn't really go there in finding the most general, for example, deformation you can add. Yeah. Thank you.
I have a question. Is this a unitary process? That means, is it reversible in time or not?
Yeah, so Rule 54 by itself, it's reversible. Then the quantum deformation, you can make it unitary or stochastic because this is the matrix that is now governing your dynamic. So you can say, you can make this F00 unitary, and then all the dynamic will be unitary, or you want to focus on stochastic deformation, so you can impose that these two sum to 1. It's really very general. These 4 parameters are can be complex, can be anything.
I thought maybe it is related to what the model, series of the models which are called directed percolation or something like that, no? Looks like a percolation.
Yeah, maybe, yeah, but I'm not fully sure. I mean, yeah, this name sounds familiar, but I cannot really say if it's related. Maybe it is related, but yeah, thank you.
Thank you.
So one last question.
So thanks for a nice talk. Do you have any hints of what could be the R matrix, even like perturbatively, if you know the Lux operator, or?
Yeah, so the problem is that now this Lux operator, it is acting on 2 legs. The first one is acting on 2 Hilbert space, so like 4 to the square, and the other one is like just 4 by 4. But then if you go into the RLL, the R matrix is acting on 2 spaces, and both of them are squared. So it will be a matrix of 4 to the 4th. Now, you can try like to take this equation and write it perturbatively, and you probably will get this R. So if you fix V equal to 0, there is a conjecture in the paper by Thomas and Balash that the R factorize as product of 2 Lux operator. And from here it also follows trivially that if you put V to 0, then you will get just identity. But higher order, I'm not really sure, we didn't try.
And you also don't know if it's difference form or not?
Probably it will be non-difference form for the way these medium range model are constructed. Yeah.
Thanks.
Another way that we have also attempted, but we didn't go very far, is to try to solve the Sutherland equation. Because you can take Yang-Baxter equation, take the first derivative, and you will get the Sutherland. And then you can use the fact that the first derivative of the Lux is, and if you put U to 0, it will be the charge Q6 that you have. So you use Q6 as input and get the R, but then it's hard because it involves R and also the first derivative of R. So yeah.
Thanks.
Thank you. If anyone has any clue on how to show the full integrability, I will be very, very happy to hear.
Thanks. Let's thank Chiara again. Our next speaker is Tim Meyer, who will tell us about integrability in angular dipole deformed n=4.
Right, thanks for the chance to speak about this project that I had together with Stein van Tongeren. And there's actually a paper that should appear in the next days about that. So this topic is, well, it starts from this ADS-CFT correspondence, especially in the case where it relates the ADS5 string to n=4. So both of these models, they share the same kind of symmetries, and they are both integrable, which especially on this on the field theory side means that we have some control over the 2-point functions via some integrable spin chain picture. As Sibylle was already mentioning in her talk, people got attracted by a kind of integrable deformations, especially these so-called homogeneous Yang-Baxter deformations as deformations of the string theory side. So this leads to some deformed class of these models, which are now symmetric under some kind of twisted symmetry. And there's a conjecture that if you apply the same kind of twisting to the field theory side, that you get a deformed theory here that should correspond to these homogeneous Yang-Baxter deformations. Right. So in this talk, I will now tell you a little bit for this particular example of this angular dipole twist, how to get this deformed theory, and then I will shed some lights on this question marks here on observables, especially the two-point function, and how to find spin chain integrability in there. Okay, so how do we actually deform this theory? This we do by deforming the product between fields. So first we formalize this pointwise, so this normal pointwise product between fields by introducing this map mu, which is just a fancy way to rewrite this pointwise product. It's now acting on this tensor product of two functions, and we can then introduce an object that is called a Drinfeld twist, which then defines a new twisted product on fields. And it's just the composition of this pointwise product mu and this inverse twist function. Okay, this twisted product is then what we call a star product, and we simply just write f star g. It turns out that this is non-commutative, but it remains associative. Well, and the idea of this deformation is then to replace every product in the undeformed theory just by all these star products in principle. To give you some examples, one relatively famous example is such a twist here, which leads to the so-called beta deformation. So this twist is basically just built from this exponential of internal R charges. So the star product then just introduces some phase factors in front of the product of two fields, depending on the charges measured by these Qs here. We can also replace these Qs by space-time symmetry generators, for example, translation generators, and then this star product introduces a non-commutativity between coordinates. So this would lead to true non-commutative field theories in the end. The twist that I would like to present now is something in between. So it's built from an internal R symmetry charge Q and a rotation generator in the 2-3 plane of space-time. And this is then what we call the angular dipole deformation. The star product then basically shifts the angular argument in this 2-3 plane of the individual fields by something that is proportional to the charge measured by Q of the opposite field. Okay, so if these fields are now, like in n equals 4, fields in some adjoint representation of a gauge group, from this expression it's already clear that this quantity here is not a nice object under normal gauge transformations. But we just follow the guiding principle and replace product by star products, considering star gauge symmetry instead. So an adjoint scalar field now, for example, transforms with a star commutator instead the normal commutator. Similarly, we can define a gauge 1 form that now transforms as such, and this also defines an exterior covariant derivative. Okay, having that, we can then write down a deformed action for Young Mills, for super Young Mills. This is how it looks like, and also here in principle, products are just replaced by star products. So this is now the deformed action. It's gauge invariant, and we can start doing field theory computations with it. So for example, we could try to look at two-point functions of gauge invariant operators. But for this, we first have to define gauge invariant operators, because the usual construction with single trace operators is not gauge invariant anymore. So in principle, we can take the trace of such a star product sequence of fields, but it's just not gauge invariant, because this star commutator here, so the star product shifts the argument of this gauge transformations that appears here, but in different ways, depending whether it appears after or in front of the star product sequence. So those things, they don't cancel against each other. What we can do to cure this is to introduce a Wilson line that now goes on a circular path in the 2-3 plane, which only has the task to cure, in principle, this difference here and bring those positions back to the same, so that these things can cancel. But this means that in every kind of gauge invariant operator, we now have to include these Wilson lines. Okay, but these are then the operators we want to compute two-point functions of, and in which we now want to find some kind of twisted spin chain picture in the end. Okay, as you might be familiar with, in pure n equals 4, you have the spin chain picture which is which has cyclic spin chains. So we would like to see whether we also have some what's happening when we move fields around this trace here in these operators. And in fact, we can move one of these fields, for example, from the front to the end, so this phi1, but then the star product is now acting in the opposite direction, and we have to account for this change by introducing such a boundary twist here. Here, this capital lambda is in principle proportional to the R charge measured of all these fields together, and lambda 1 is just measuring the R charge of the field that is moved, in this case phi1. Similarly, these M23s here, they act as Lie derivatives on the appropriate fields as well. I said they act as Lie derivatives, which means they have in principle two parts. One acts as a partial derivative with respect to the angle in the 2-3 plane, and the other measures in principle the physical spin of the particles. So we would like to translate now these things to spin chain language. This immediately works for this spin measuring part. This has a clear definite meaning in terms of spin chain language, but these partial derivatives, they don't have such a meaning immediately. And similarly also these Wilson lines, they just don't appear in the spin chain picture of n=4. So what we do is to restrict the space-time dependence of our operators to be just in the 0-1 plane. If we do that, then these Wilson lines, which go on circular paths in the 2-3 plane, they shrink to a point and become trivial. And similarly, also these partial derivatives here, they trivialize. So this is the only thing that is left over from these boundary conditions. And now all these things, they have a definite meaning in terms of the spin chain. So we can then write down the planar one-loop Feynman diagrams that appear in the two-point function of these operators, and it turns out that they arrange themselves in the same kind of sums of nearest neighbor interaction that we find in the undeformed n=4 as well. So we can actually reuse the same kind of spin chain picture that we have in the undeformed case, where we just have the same nearest neighbor spin chain Hamiltonians. But now these gauge invariant operators that we have, they are now corresponding to some kind of cut open spin chains, where whenever we move a spin over this cut, we have to account for this change by imposing twisted boundary conditions. The anomalous dimensions of these, the planar anomalous dimension at one loop of these operators then can be shown to, or this is actually what we did, then correspond to the spectrum of this Hamiltonian, which, like in the undeformed case, is the sum of all these nearest neighbor Hamiltonian. But again, we have to account for this twisted boundary condition for this one interaction that acts over this slit here, this cut. So such twists, they are also known in the literature, and they are shown to be integrable, and they can be solved using beta ansatz and beta equation. So that means that in this two-point function of our gauge invariant operators, we really found some kind of deformed or twisted spin chain integrability in this picture. So, right, in this angular dipole deformation, we now have this kind of integrability picture, and even more excitingly, we find the same kind of beta equations and beta ansatz also for the spectrum of the appropriately deformed string theory side. So this correspondence for these examples really seem to survive this deformation process, which strengthens this conjecture for these models. Okay, thanks.
About the deformed beta equations, could you say a few words how they look like, how do they deform, does the spectrum change? And also, can you write down the deformed R matrix here?
This work is, these spin chains, they have been known quite a while, and there's actually a paper by Beisert and Reuban who did this. And so there, in principle, it is exactly that spin chain.
Thanks for the talk. I was just wondering, so with Drinfeld twisted spin chain, a lot of, well, always, you should have a mapping between deformed picture and then undeformed with twisted boundary condition pictures. But here it seems that you're landing straight on the twisted spin chain. How does the deformed picture look like also from maybe from the gauge theory side? Because
that's a good question. So maybe to explain why this is reasonable for us. So I mean, to land in this picture, the guiding principle is that we want to have gauge invariant quantities, and so it's natural for us to think in this star gauge symmetries, and it's just a natural it seems to be a natural consequence of that we end up in this twisted boundary picture. Anyway, there is something that is called a Seiberg-Witten map, which exists for these non-commutative field theories, and you can then express these star gauge symmetric fields, or star gauge fields, I would say. You can express them in terms of normal gauge theory fields in principle. And if you would, so the conjecture here, and like for these dipole deformations, you can actually show that if you use those fields instead to define different bases of operators, then this is where you find the twisted spin chain picture and not the boundary, twisted boundary picture.
So the twisted boundary conditions you have, do you fall under diagonal twists, or sometimes you find more general types?
So, like, I mean, since we here started from a twist that is diagonalizable, like it's basically measuring charges of the fields. Well, it's really like just in principle in the spin chain language imposing phases. But the idea is, and this is also what we did work on, when you consider more involving twists, proper non-commutative twists, for example, you can also think on non-diagonalizable twists, kind of. But this is an open question whether these really then the field theory really follows the kind of expectation from spin chains.
Thanks. There's one question from Kolya.
So in this formula, do you see double trace terms appearing naturally? I just don't remember.
So you mean in the action, or kind of like you're thinking of beta deformation where you also have the double trace interaction, right? It's a good question. Like these things, they in principle we cannot exclude that we would need some corrections like this in the action to make the theory like have a proper scaling dimension. But the thing is, there's a paper already in the beta deformation that these things at the planar limit just play a role for very, very short operators. So as long as we consider something of length 3 or longer, we wouldn't expect those to appear. That's a good question. So in principle, this is something I'm also interested in and I would like to look at. It was just recent that we were even able to formulate these theories consistently. So it's an open question whether there exists an interesting limit and how to take this. It would definitely look relatively different from the normal fishnet limit, because it's harder to say that you have some interactions that are untouched by this. Like in the fishnet limit, for example, by taking this limit, you can strip off the gauge fields, for example. Something like this is, from my perspective, a little bit unlikely to happen in these deformations.
Okay, if there are no last questions, okay, let's thank Tim again. Our last speaker is Elisabetta Armanini. She will tell us about scattering on the Coulomb branch of N=4 Supriam Mills.
Hi everyone, thanks for giving me the opportunity to speak. It's a pleasure for me to talk about this ongoing work with Fernando Aldai, Kilian Herring and Sasha Ziboedov.
So an interesting object that we would like to study and understand more is the gauge theory flux tube. And we know that thanks to the gauge and string duality, this is dual to an open string, which extends in the radial direction of ADS. So in order to probe the dynamics of these objects, we are going to consider the following observable. A 4-point amplitude of open strings that end on a probe D3 brane that is placed at some position Z different from 0 in ADS 5 cross S5. This setup on the gauge theory side is dual to planar n equal 4 superior Mills on the Coulomb branch. This is just an X version of n equal 4 that can be obtained by giving a vacuum expectation value to the scalars, as Shota was explaining yesterday. So this is the amplitude, the object that we are going to study in this work, and let's see what are its properties. So if we consider the Toft coupling to be small, we can compute the amplitude using perturbation theory. So for instance, at one loop is given by this box, where here in the frame we have some massive W bosons of mass m. So already at one loop, you can see that this amplitude has a two-particle cut starting at 4m squared. But the most interesting property of this amplitude is that not only it has a two-particle cut, but it also has a set of bound states. And these bound states appear as we increase g. And the reason is that the physical problem that we are studying is the one of the Coulomb potential. And indeed, as was studying this work by Caron and Hen, we can actually match the bound states at weak coupling of this amplitude to the bound states of the non-relativistic hydrogen atom. Also at strong coupling, we have some control on the amplitude. So if we take the Toft coupling to be large, and we take the soft limit, so small s and t, the leading contribution to the amplitude is given by the flat space 3-level scattering, and this is given by the very famous Veneziano amplitude. Then, of course, we can also have 1/g corrections, as we heard this morning, so these are going to probe the radius of ADS, and we managed to compute this correction here using the worldsheet bootstrap. The most interesting part, though, comes at finite g. So here we don't know anything about the amplitude, and what we would like to do in this work, so our goal is to combine 3 ingredients to be able to say something about the amplitude at finite coupling. In particular, we are going to use dual conformal invariance. This is an extra symmetry of this theory in the Coulomb branch. We are going to combine it with integrability and then with the symmetrics bootstrap. So let's see how to combine these 3 ingredients all together. In order to do that, it's important to talk about Regge trajectories because these are an important topic to characterize the physics of the scattering amplitude. So let me remind you that, for instance, Regge trajectories in string theory have a very simple structure, so they are just straight, while, for instance, in other theories like large N QCD, they can also bend. In our case, Regge trajectories have a very peculiar form. So in particular, they bend, and they also diverge, and they diverge at s equal 4m squared. So this is the position of the ionization threshold, because for s bigger than 4m squared, we have a two-particle cut, so we have the continuum. And the reason why these Regge trajectories diverge is because we have an ADS horizon. Then when s is large and negative, here the leading Regge trajectory goes like a log, as was studied in this paper. But the most important property of Regge trajectories in this theory is that thanks to dual conformal invariance, the computation of Regge trajectories can be mapped into the computation of a cusp anomalous dimension of a Maldacena-Wilson line in n equal 4 superior Mills with eventual operator insertion in the cusp. So this relationship is very precise, and it goes as follows. So the leading Regge trajectory is equal to the cusp anomalous dimension of a Maldacena-Wilson line with cusp angle phi, and the cusp angle and the Mandelstam S are related in a precise way. The subleading trajectory J1 is equal to a cusp anomalous dimension of a Maldacena-Wilson line with an operator insertion in the cusp. This operator is a scalar, and this is the same scalar that couples to the Wilson line. So this is why we call this phi parallel. So it's very interesting to see now how different limits of the Regge trajectory, in particular the leading one, can be captured by different physical quantities on the Wilson line side. So for instance, here the intercept is -1. Then when we turn on the cusp angle to be small, we see the Brent-Stralium function B. When phi goes to pi, we have the quark-antiquark potential, while when s is large and negative, we have to analytically continue the cusp angle to be Lorentzian. When we send it to infinity, we see the light-like cusp. For the subleading trajectory, we have a similar structure, but it's a bit different because here we have a critical coupling, as was already studied in this paper. And below this critical coupling, the subleading trajectory does not diverge. So this means that below this critical coupling, we do not see any excited bound state. The punchline of this radio trajectory discussion is the fact that these right-hand sides here can be computed using integrability of n equal 4 super-Young mills, but in particular for any value of the coupling and of the cusp angle using quantum spectral curve, as was developed by Kolya and a lot of people in this room. So now we have a way, thanks to dual conformal invariance and integrability, in particular quantum spectral curve, to compute the position of the bound states on the leading trajectory and on the subleading trajectory, and these will be useful inputs in the S-matrix bootstrap. So dual conformal invariance has also another important consequence regarding unitarity. So this dual conformal invariance, you have to think about it as an extra symmetry. And as you know, if we take, for instance, the case of the hydrogen atom in quantum mechanics, we have the usual SO3 symmetry. But if we combine it with the Runge-Lenz hidden symmetry, this enlarges the SO3 symmetry group to be SO4 on the bound states and SO1,3 on the scattering states. So our case is actually a relativistic generalization of this. So we have to take our SO3 symmetry and we combine it with dual conformal invariance. And this allows to expand the imaginary part of the amplitude. Instead of using SO3 partial waves, we are going to use these enlarged symmetry groups. So SO4 partial waves on the bound states, when S is between 0 and 4m squared, and SO1,3 partial waves on the cut. So this is a new, let's say, enhanced version of unitarity. And this will be, as you will see in the bootstrap, stronger than the usual SO3 unitarity. So now the idea is to use the knowledge that we have coming from integrability of the spectrum of bound states and this enhanced unitarity to use them in the bootstrap to put some bounds on our amplitude. In particular, the usual observables that we bound into the S-matrix bootstrap are Wilson coefficients. So these are the EFT couplings that appear in the low energy expansion of the amplitude F. And let me point out that two of these coefficients are actually already fixed. So we have this 1 over ST given by the 3-level Gluck exchange. And then we have A00, which is one loop exact thanks to a Norren normalization theorem from supersymmetry. So our target is to bound A10, A20, A21, or suitable ratios of them by using S-matrix bootstrap. And the way to do it is using dispersion relations. So the fact that we can write the scattering amplitude as an integral over its imaginary part. So we have an integral over the bound states. Here we are going to use SO4 partial waves and the knowledge of the spectrum coming from integrability. And then we have an integral over the cut where we are going to use SO1,3 unitarity. So let me show you some bootstrap bounds. So for instance, this is a bound on A10 divided by A00 as a function of the coupling G. So as you see in blue, this is the allowed region given by the bootstrap. And this is compared with a Padé band that we generated using weak coupling expansion, strong coupling expansion data, and then some error model. So I want you to notice three important things. So first of all, this Padé band is compatible with the bootstrap bounds, so is inside the bounds. Then when G is equal to 0, you see that the lower bound is actually equivalent to the weak coupling data. And this can be seen better if we do this 2D plot, A10 versus A20. So we want to see what is the allowed region for this plot. Using SO3 unitarity, we find this region here encoded in this black line. But if we use SO1,3 unitarity, you magically see that the region shrinks, and there is a kink and a minimum, and this minimum precisely corresponds to n equal 4 super-Young mills at one loop. So this was a surprising result because we saw that n equal 4 super-Young mills at one loop on the Coulomb branch is extrema. Then here, notice that at strong coupling, the upper bound, our upper bootstrap bound, goes closer and closer to the strong coupling data. So, of course, these bounds can be actually improved. These are all preliminary plots, but we need some further inputs from integrability or, for instance, from localization. But I hope I convinced you that by combining dual conformal invariance, integrability, and the S-matrix bootstrap, we can derive some non-trivial bounds at finite G on this very interesting amplitude. Thanks.
Strong coupling. So could you say more like how you computed that?
Yeah, so basically, so you have to, as Maria was saying this morning, so you make an ansatz using like a worksheet integral. And then you make this ansatz where you say this, you write your worksheet integral times a function, and this function has to contain harmonic polylogs up to some weight, in particular weight 3. And then we call it worksheet bootstrap because then you're going to use some inputs coming, let's say crossing, the usual things, but also we are going to use some inputs coming from integrability. So for instance,
well, okay, wait, sorry. So just to clarify the question, so usually with that algorithm, on one side you have a worldsheet ansatz, and on the other side you have a CFT with a block expansion. But in this case, you don't have a CFT.
Exactly. Yes.
So I'm wondering what's the other side.
Exactly. Yeah. So we don't use the CFT because conformal symmetry is broken, as you said, and so we had really to start from scratch. If you want, we make an ansatz. This is this worldsheet integral. We have a function, and then we expand this function. And we have to fix the coefficients in this function using some inputs, for instance, coming from integrability. And this actually fixes the ansatz in a non-trivial way. I mean, we can discuss more, but Fernando input was very useful in this, and yeah.
There's one question from Judith.
You said more input from integrability would be useful. What exactly would?
Well, for instance, like the 3-point couplings. If there is a way to compute the 3-point couplings, so the residues on the bound states using integrability, this would be helpful to put in the bootstrap. But I think it's very hard.
On the spectrum side, do you need?
No, on the spectrum side, no, because we already have the leading trajectory, the subleading one, and then knowing the sub-subleading is actually not so important for the numerics. So.
Does this relation with the cusp survive for example, excited states? You can have the cusp with operators inserted.
Yeah, so, well, we have a conjecture that this holds to be true also for subleading trajectories, but then you have to consider some operators that are these operators in 1D CFT, these L000 operators. But for now, we have we see that this works just when S is equal to 0, so when phi goes to 0. So it's actually non-trivial to generalize this for a general cusp. So, yeah, but it's a very interesting part to study and understand more how it works at subleading orders.
Thanks.
Perhaps my question is also a confusion that I have. I thought that when we were doing like this, I know this Coulomb branch amplitudes or something like that, we should see, at least for 4 points, we should see some sort of gamma octagon instead of some gamma cusp, right?
No, this is a different limit. Yeah, the octagon actually, if I'm not mistaken, appears if so these guys for me are massless and these are massive. The octagon, I think, is the opposite way
around.
It's
the other order, I see,
yeah.
I see.
There are other questions? If not, let's thank Elisabetta again and all the speakers of today.
Mike's